What stirred the first spark that turned nothingness into the expanding cosmos? How did tiny quantum ripples in the newborn universe grow into galaxies and stars? Why did matter win its fragile victory over antimatter in the first moments of time? In the beginning, there was no sunrise to mark a morning, and no horizon to measure distance. There was no canvas of space for stars to adorn, and no river of time to carry moments forward. Instead, there was a profound stillness, a state beyond comprehension, where the very idea of before and after did not apply. It was a moment when the universe was not yet born, and yet all potential was contained within a pointless void, waiting to unfold. One can imagine that in that primordial absence, there were fluctuations in fields at scales too small for our current physics to describe. The Planck time and Planck length are names we give to this realm where quantum mechanics and gravity dance inseparably. At such scales, the concept of energy loses its familiar meaning, and space and time may have behaved like frothing foam. We have no measurements from this epoch. It is an intellectual horizon, beyond which theory is largely speculative. The idea of a singular beginning arises from extrapolating backwards the expansion we see today. If the universe has been expanding for billions of years, then at earlier times it must have been denser and hotter. Projecting this trend leads to a point of infinite density and zero volume, which we call a singularity. Yet many physicists believe that before reaching infinite density, new physics would intervene, perhaps smoothing out the singularity or replacing it with a quantum transition. Out of that abyss, an event occurred that defies ordinary intuition. In an instant, the calm was broken by an emergence that set time itself into motion. A seed of unimaginable energy erupted, and space began to stretch, not into existing emptiness, but bringing emptiness into being. The universe expanded at a rate so swift that a tiny quantum fluctuation was magnified to cosmic dimensions, a brief inflation that wrote the pattern of structures yet to form. This early expansion is thought to have been driven by a peculiar form of energy inherent to space itself. Known as vacuum energy, it has a repulsive gravitational effect, causing space to push on itself and expand. During inflation, this energy density remained nearly constant, even as space ballooned at an exponential rate. The universe grew from subatomic scales to macroscopic size in a tiny fraction of a second, smoothing out any curvature and irregularities. Inflation also solves what is known as the horizon problem. In our observable universe, regions separated by vast distances have almost identical temperatures. Without inflation, those regions would never have been in causal contact, making such uniformity puzzling. By expanding faster than light could travel, inflation allowed regions that were once close together to be stretched far apart, explaining why they share the same temperature. It also flattened the geometry of space, matching observations of a nearly flat cosmos. During this extraordinary expansion, the distances separating points exploded, smoothing out irregularities, yet allowing tiny ripples to survive. Those ripples were fluctuations in the quantum fields, minute variations that carried the blueprint for galaxies and stars. As space ballooned and the cosmos cooled, these fluctuations imprinted gentle variations in density that gravity would later amplify. The rapid inflation solved the puzzle of why the cosmos appears uniform and why distant regions share the same conditions despite never being in contact. Quantum mechanics tells us that fields cannot be perfectly uniform. They must fluctuate even in their lowest energy state. Before inflation, these fluctuations occurred on scales smaller than atomic nuclei. As inflation stretched space, the wavelengths of these fluctuations were stretched far beyond the size of galaxies. When inflation ended, these ripples froze into differences in density, with some regions slightly denser than others. These seed perturbations are visible today as tiny temperature variations in the cosmic microwave background. Another mystery addressed by inflation is the flatness problem. If the density of the universe were even slightly greater or lower than a critical value, its geometry would curve drastically, and the cosmos would have either recollapsed quickly or expanded so fast that structures could not form. Inflation drove the universe toward this critical density, ironing out curvature and leaving a flat geometry. This process allowed the universe to survive long enough for galaxies, stars, and life to emerge. The violent growth lasted a fraction of a blink and then slowed, leaving behind a universe filled with pure energy. At first, all the fundamental forces were indistinguishable, unified in a primordial symmetry at energies beyond anything we can replicate. But as the temperature dropped, this symmetry shattered. Gravity separated from the other forces, taking on its role as the slow curving of spacetime that would sculpt galaxies and hold planets in their orbits. The separation of gravity occurred incredibly early, at the unimaginably small Planck time. Before that moment, we cannot meaningfully discuss gravity in isolation. Once it decoupled, gravity began to act independently, shaping the evolution of the universe. The remaining forces, strong, weak, and electromagnetic, remained unified for a time. Theories like grand unification suggest that at extremely high energies, these forces were manifestations of a single interaction. As the universe cooled, this unity broke down through symmetry breaking. Symmetry breaking is a concept where a system governed by symmetrical laws ends up in an asymmetric state because certain configurations are energetically favorable. In particle physics, fields take on specific values that minimize potential energy. During cooling, a field associated with the strong force settled into a state that distinguished it from the electroweak force. The strong force would then exclusively bind quarks inside nuclei, while the electroweak force would later split into electromagnetic and weak components. Soon after, another division occurred as the strong nuclear force decoupled. The strong force would later bind quarks into protons and neutrons, giving rise to the hearts of atoms. In that brief interval after separation, energy condensed into exotic particles that would vanish as quickly as they appeared. Quarks and antiquarks danced in a seething plasma alongside leptons and gauge bosons, constantly colliding and transforming as the universe remained hotter than the core of any star. The era when the strong force became distinct from the others is known as the Grand Unification Epoch. During this time, the universe was filled with a quark-gluon plasma in which quarks roamed freely, not yet confined within hadrons. As temperatures fell, quarks began to bind into composite particles, such as protons and neutrons, but only after the quark epoch ended. Exotic heavy particles like X and Y bosons, predicted by some grand unified theories, may have existed fleetingly. Their decays might have contributed to the slight surplus of matter over antimatter. As the universe expanded, these heavy particles decayed, and the energy was redistributed among lighter particles. The creation and annihilation of particle-antiparticle pairs continued, maintaining a thermal equilibrium. The slight asymmetry that favored matter persisted because certain interactions violated combined symmetries of charge and parity. This breaking of CP symmetry could be responsible for the survival of matter, though the exact mechanism remains an open question in physics. At such extreme energies, matter and antimatter were created in almost equal numbers, For every particle, there existed a mirror, opposite, with the same mass, but opposite charge. When particles and antiparticles met, they annihilated and produced light. Yet for reasons still mysterious, there was a slight excess of matter. This tiny imbalance, perhaps one particle in a billion, ensured that some material remained after most pairs annihilated. Without that asymmetry, the universe would be filled only with radiation, and nothing tangible would exist. During the electroweak epoch, the electromagnetic and weak forces were still unified. As the universe cooled to energies below that unification scale, the electroweak force split. This separation allowed the W and Z bosons, carriers of the weak force, to acquire mass, whereas the photon remained massless. The Higgs field, permeating space, acquired a non-zero value, and through its interactions, particles gained their masses. The universe now contained massive quarks and leptons, as well as massless photons and gluons. Not long after, the quark epoch gave way to the hadron epoch. Quarks combined to form hadrons, protons and neutrons, when the temperature fell enough for the strong force to confine them. Free quarks ceased to exist, locked forever within these composite particles. Neutrinos, nearly massless and weakly interacting, decoupled from matter and began traveling freely through space. Their decoupling marks the birth of the cosmic neutrino background, a relic as ancient as the microwave background, but much harder to detect. As the cosmos cooled further, the quark soup transitioned. Quarks began to feel the grip of the strong force, pairing into protons and neutrons in the first microseconds. The four forces, gravity, strong, electromagnetic, and weak, assumed their distinct identities. The weak force mediated the decays of heavy particles and allowed neutrinos to slip free. The electromagnetic force bound charges and later would govern chemistry and light, while the strong force bound quarks within protons and neutrons. By the end of the hadron epoch, most energy existed in the form of radiation, photons and neutrinos, with a smaller fraction as matter. The next era, the lepton epoch, was dominated by leptons, including electrons and positrons. These particles were abundant, and their continuous annihilation produced a flood of photons. As the universe expanded and cooled further, positrons annihilated with electrons, leaving a tiny excess of electrons to balance the positive charge of protons. This leftover ensures the universe is electrically neutral on large scales. As fractions of seconds passed, the universe continued to expand and cool. Protons and neutrons collided, forming light nuclei in a process known as nucleosynthesis. This fusion occurred within minutes when the temperature fell enough for these collisions to stick. Deuterium, a combination of one proton and one neutron, formed first. Deuterium then fused into helium nuclei containing two protons and two neutrons. A trace of lithium and beryllium also formed, but most matter remained as simple hydrogen. Nucleosynthesis required a delicate balance between expansion and reaction rates. If the universe had expanded more quickly, deuterium would not have survived long enough for helium to form. If expansion was slower, more helium and heavier elements would have been produced. Observations of primordial helium and deuterium abundances provide a stringent test of cosmology. The measured fraction of helium, about a quarter of the mass of normal matter, matches predictions from this early synthesis. Trace amounts of lithium were also created, though observations show a discrepancy known as the primordial lithium problem. The slight imbalance between neutrons and protons at the onset of nucleosynthesis influenced the outcome. Neutrons are slightly heavier than protons and can decay into protons with a lifetime of around 15 minutes. During the cooling, some neutrons decayed before combining into nuclei. The resulting ratio of neutrons to protons determined how much helium could form. because neutrons largely ended up inside helium nuclei. The abundance of helium provides indirect evidence of how many neutrons were present. By the end of this brief window, the composition of the universe was set. Roughly 3 parts hydrogen to 1 part helium by mass, with just whispers of heavier elements. The abundance of helium would be a lasting signature of these first minutes. After about 20 minutes, the expansion and cooling halted this primordial fusion. The universe was left filled with an intense glow of light and neutrinos, but the building blocks of future stars were now present. Once nucleosynthesis ceased, the universe entered the photon era. Photons dominated the energy density and continued to interact vigorously with free electrons and nuclei. Matter existed mostly as a plasma, a soup of charged particles constantly scattering light. This scattering is described by Thomson scattering, a process in which photons bounce off charged particles without losing significant energy. Because of this, photons could not travel far. They were trapped in a fog, constantly reabsorbed and re-emitted. During this photon-dominated era, the universe was opaque, like the interior of a star. Although it was filled with light, that light could not escape. As the cosmos expanded, the wavelength of photons stretched and their temperature decreased. Yet because they could not travel freely, they maintained thermal equilibrium with the matter. This state persisted for hundreds of thousands of years until the conditions allowed atoms to form and release the photons. In the absence of free quarks and the end of the nucleosynthesis era, the cosmos entered a period dominated by radiation. Photons streamed through a dense plasma of electrons, protons, and helium nuclei. Every time a photon tried to travel, it scattered off a charged particle. This scattering kept the universe opaque. Light could not travel far before bumping into matter. The universe was a bright but hidden fireball, shining intensely, yet unable to release its light. The pressure of radiation played a significant role in shaping the early universe. Photons exert radiation pressure, pushing against matter and preventing gravitational collapse on small scales. Meanwhile, dark matter, which interacts only through gravity, began to clump under its own weight. The interplay between radiation pressure and gravity set the stage for future structure formation, leading to acoustic oscillations in the plasma that would leave imprints in the cosmic microwave background. These oscillations can be thought of as sound waves rippling through the primordial plasma. Regions of higher density were compressed by gravity, raising temperature and pressure, causing them to expand. This expansion decreased the density, allowing gravity to compress them again. The cycle continued, creating standing waves whose scales are imprinted in the temperature fluctuations of the microwave background. Today, we observe these patterns as peaks in the power spectrum of cosmic microwave background anisotropies. During this radiation-dominated era, neutrinos, those ghostly particles that rarely interact, decoupled from matter. They slipped away and continued to stream across the cosmos, carrying with them information about those earliest seconds. Electrons and positrons annihilated each other, leaving a slight surplus of electrons that would later enable atoms to form. The ratio of neutrons to protons gradually shifted because neutrons decayed into protons and electrons, altering the final composition of helium. The decoupling of neutrinos occurred when the density and temperature fell to a point where weak interactions could no longer maintain equilibrium. From that moment on, neutrinos traveled essentially unimpeded, forming a cosmic neutrino background, analogous to the cosmic microwave background. Although we have not yet directly detected this neutrino relic, its existence influences the expansion rate and leaves subtle signatures in the cosmic microwave background that confirms its presence. Electrons and positrons, meanwhile, continued to annihilate each other until the temperature fell below their rest mass energy. This annihilation transferred energy into photons, heating the radiation bath relative to the neutrino background. The leftover electrons determined the number of electrons available to combine with protons during recombination. The delicate interplay between particle interactions and expansion shapes the observable universe we see today. As hundreds of thousands of years unfolded, the universe continued to cool. The temperature dropped from billions of degrees to thousands. Eventually, electrons slowed enough to be captured by protons and helium nuclei. When a proton captured an electron, they formed a neutral hydrogen atom. Similarly, helium nuclei captured electrons to form helium atoms. This process is known as recombination, although it was truly the first combination of these particles. Recombination did not occur instantaneously, but over a range of times and temperatures. Hydrogen and helium have different ionization energies, so helium captured electrons earlier than hydrogen. As each hydrogen atom formed, it emitted a photon, which could ionize another nearby atom. This complicated interplay delayed the completion of recombination. Nonetheless, by around 380,000 years after the beginning, most electrons were bound into atoms, and the universe became largely neutral. The term recombination is a historical misnomer because it implies a second combination, but no prior combination took place. Scientists use it to describe the stage when the plasma recombined to form neutral atoms. As atoms formed, the free electron density dropped dramatically. Photons scattered less frequently and eventually decoupled from matter, free to travel vast distances. The universe transitioned from opaque to transparent in a relatively short period. The moment electrons bound to nuclei, the charged plasma transformed into neutral gas. Photons that had previously ricocheted off electrons were now free to travel vast distances without constant scattering. The cosmic fog lifted, and the light that had been trapped within the plasma streamed outward in all directions. That light has traveled for more than 13 billion years and now pervades the universe as the cosmic microwave background. The surface from which these photons last scattered is often called the last scattering surface. Because the universe has expanded since recombination, these photons have been stretched from visible or infrared wavelengths to microwave wavelengths. The redshift of the cosmic microwave background records how much the universe has expanded since that time. When we observe this background today, we are looking at a spherical shell of space as it existed long ago, much like seeing the surface of a bubble from within. Tiny variations in the cosmic microwave background provide a wealth of information about the early universe. Slightly warmer regions correspond to denser areas that would evolve into galaxies and clusters. Slightly cooler regions indicate underdense areas that would become cosmic voids. The statistics of these temperature fluctuations match the predictions of inflationary models remarkably well. They also allow us to infer the geometry of space, the composition of the universe, and the nature of primordial fluctuations. The cosmic microwave background is a faint glow that fills the sky, invisible to our eyes, but detectable with radio instruments. Today, its temperature is a chilly 2.7 Kelvin, just a few degrees above absolute zero. It preserves a picture of the universe at the time of recombination, showing tiny temperature variations corresponding to the density fluctuations seeded during inflation. Those variations reveal the seeds of all galaxies and clusters we see today. The measurement of the cosmic microwave background's temperature and anisotropies has progressed through several generations of experiments. The Cosmic Background Explorer, COBE, satellite first measured its near-perfect blackbody spectrum in the early 1990s, confirming the Big Bang prediction. COBE also detected anisotropies on large angular scales, revealing the imprint of primordial fluctuations. Later missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite mapped the background with greater precision, revealing acoustic peaks and providing tight constraints on cosmological parameters. In addition to temperature variations, the cosmic microwave background is polarized. Two types of polarization patterns, known as E modes and B modes, encode information about different phenomena. E modes arise primarily from density variations and reionization, while primordial B modes could arise from gravitational waves generated during inflation. Detecting these B modes is an active area of research and could provide direct evidence of inflation and the energy scale at which it occurred. The existence of this ancient light remained unknown until the mid-20th century. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were calibrating a horn antenna when they discovered persistent microwave noise. They eliminated all sources of interference, even cleaning pigeon droppings from the equipment, yet the noise remained. At the same time, a group of physicists predicted relic radiation from the Big Bang at around 10 degrees Kelvin. When Penzias and Wilson shared their puzzling observation, the physicists realized that the cosmological afterglow had been found. This serendipitous discovery was soon recognized as a milestone in cosmology. Penzias and Wilson did not initially know that they had detected the afterglow of the Big Bang. It was the theoretical work of Robert Dicker and his colleagues at Princeton that provided the context. They had been constructing their own microwave receiver to search for the cosmic radiation predicted decades earlier. Upon learning of the Bell Lab's noise, they realized it was exactly what the Big Bang model predicted. The observation by Penzias and Wilson was quickly confirmed by other experiments. Their work earned them the Nobel Prize in Physics in 1978. The cosmic microwave background became the cornerstone evidence for the hot Big Bang theory, shifting the cosmological community's view. Before its discovery, alternative ideas like the steady-state model competed with the Big Bang. The uniform background radiation strongly supported an origin from a hot, dense state and undermined steady-state theories. The discovery of the cosmic microwave background provided compelling evidence for the Big Bang theory. It demonstrated that the universe was once hot and dense, and has been cooling and expanding ever since. Subsequent measurements refined the temperature to 2.7 Kelvin and mapped the tiny variations across the sky. These observations matched the predictions of cosmic inflation, confirming that quantum fluctuations were magnified to seed cosmic structures. The microwave background is a snapshot of the infant universe, preserved on a canvas of cold light. The cosmic microwave background also allows us to determine the age and composition of the universe. By comparing the observed anisotropies with theoretical models, cosmologists infer the proportions of dark matter, dark energy, and normal matter. The data indicate that ordinary matter makes up only about 5% of the universe's energy budget. Dark matter accounts for roughly 25%, providing the gravitational scaffolding for galaxies. The remaining 70% is dark energy, a mysterious component that drives the accelerated expansion of the universe today. Beyond the cosmic microwave background, other relics from the early universe remain. The cosmic neutrino background is one such relic, though it is far more elusive. There may also be primordial gravitational waves, ripples in spacetime generated during inflation, that could be detected through their imprint on the polarization of the microwave background. Each relic offers a unique window into the first moments, carrying messages across billions of years. After recombination, the universe entered an epoch often called the Dark Ages. The name does not imply that nothing happened. Rather, it reflects the absence of luminous objects. With electrons bound into atoms, the universe was transparent to radiation. but there were no stars or galaxies to emit visible light. Space was filled with neutral hydrogen and helium gas, cooling as the expansion continued. The only light was the fading afterglow of the microwave background, stretched to longer wavelengths and dimming over time. During the Dark Ages, the 21-centimeter line of neutral hydrogen became an important potential probe. When the electron in a hydrogen atom flips its spin relative to the proton, it emits or absorbs a photon with a wavelength of 21 centimeters. Astronomers hope to detect this line from the Dark Ages as either absorption or emission against the cosmic microwave background. Such observations would reveal the distribution and temperature of hydrogen gas, providing insights into the formation of structures before the first stars. However, detecting the 21-centimeter signal is challenging because it is faint and must be observed at frequencies corresponding to high redshifts. Earth's ionosphere and human-generated radio interference add to the difficulty. Dedicated experiments and future radio arrays are being designed to measure this signal. If successful, they will map the cosmic web during the Dark Ages and trace the transition to the epoch of rayonization. During the Dark Ages, gravity began to sculpt the gas into structures. Tiny differences in density, inherited from inflation and imprinted in the microwave background, allowed some regions to have slightly more matter than others. These denser regions exerted a stronger gravitational pull, drawing in more gas and dark matter. Over time, they grew into halos, gravitational wells dominated by dark matter, with gas pooling at their centers. The cosmic web began to form as filaments and nodes of matter interconnected across space. The process of growth is described by linear perturbation theory at first, where small deviations from uniformity grow proportionally with the scale factor. As the density contrast increases, the growth becomes nonlinear, and halos begin to collapse under their own gravity. Dark matter, being collisionless, forms extended halos with densities falling off with radius. Baryonic gas, however, can cool and sink toward the center of these halos, where it may form stars under the right conditions. In the cold dark matter model, structure formation proceeds hierarchically. Small halos form first and merge into larger ones over time. This bottom-up growth leads to a network of filaments connecting nodes of high density. Within this web, voids emerge as underdense regions. This cosmic web pattern is observed in the distribution of galaxies and clusters today, confirming the predictions of cold dark matter cosmologies. The interplay between dark matter gravity and baryonic physics shapes the appearance of the cosmic web. Within these dark matter halos, gas slowly cooled and condensed. However, cooling was inefficient because the gas contained only hydrogen and helium, which do not radiate heat easily. Molecules like hydrogen molecules had to form to allow energy to escape, enabling the gas to collapse. As the gas contracted, it heated up due to compression, but radiative cooling allowed it to continue collapsing. Eventually, these clouds reached densities and temperatures where nuclear fusion could ignite. In primordial gas, the formation of molecular hydrogen proceeds through interactions between hydrogen atoms and electrons or protons. The resulting molecules emit radiation when they rotate or vibrate, providing a cooling channel. Without molecules, the gas would remain too warm and resist fragmentation. Simulations of early structure formation show that only halos above a certain mass threshold can cool efficiently and collapse. These are the sites where the first stars, known as population 3 stars, are predicted to form. The mass of these first stars is thought to be very high because the cooling channels allowed the gas to collapse into relatively large fragments. In the absence of heavy elements, cooling was limited, so the collapsing clouds did not fragment into many small pieces as they do in the present-day universe. Instead, they collapsed into a single or few massive clumps. These stars would have short lifespans and end their lives in spectacular supernova explosions, dispersing heavier elements into the surrounding gas. The first stars likely appeared a few 100 million years after the Big Bang. They were massive, perhaps tens or hundreds of times the mass of our Sun, and burned brightly. Their ultraviolet light rayonized the surrounding hydrogen, ending the Dark Ages and initiating the epoch of rayonization. Their supernova explosions enriched the gas with heavier elements, paving the way for later generations of stars and planets. But in the timeline we are tracing, the ignition of the first stars lies ahead. For now, we linger in the darkness before dawn, the quiet between the cosmic fog lifting and the first lights igniting. The ultraviolet photons from the first stars had enough energy to ionize neutral hydrogen, splitting electrons from protons. This created ionized bubbles around each star that grew and eventually overlapped. As more stars and early galaxies formed, these bubbles merged, and the intergalactic medium became fully ionized again. This epoch of rayonization fundamentally altered the transparency of the universe to ultraviolet light and left its mark on the cosmic microwave background through secondary anisotropies. Observations of the most distant quasars and galaxies provide hints of the timing of rayonization. Spectra of high redshift quasars show a Gunn-Peterson trough, indicating the presence of neutral hydrogen at early times. Measurements suggest that rayonization occurred between about 400 million and 1 billion years after the Big Bang. Future telescopes and 21-centimeter experiments aim to pinpoint the timeline of this transformation and understand the sources that drove it. This tranquil period allowed gravity to gather matter into ever larger halos. Small halos merged to form larger ones in a hierarchical fashion. Some of these halos would later host dwarf galaxies. Others would become the seeds of spiral and elliptical galaxies. Without any starlight, the universe remained cold and dark, yet the stage was being set for the fireworks of star formation. The interplay of gravity, cooling, and the first molecules determined where the first stars would appear. Mergers between halos can be violent, triggering shocks that heat the gas. These shocks compress the gas and can increase the rate of molecular hydrogen formation, thereby enhancing cooling. On the other hand, energetic feedback from the first stars and their supernovae can disrupt collapsing clouds and suppress star formation in neighboring halos. This balance between triggering and suppressing star formation introduces complexity into the transition from dark ages to cosmic dawn. The chemical enrichment from the first supernovae also changes the cooling properties of the gas. Heavy elements provide additional channels for radiation, enabling gas to cool to lower temperatures. This leads to fragmentation into smaller clumps, resulting in the formation of lower mass stars similar to those in the present day. Thus, the earliest stars set the stage for more diverse stellar populations by altering the composition of the interstellar medium. The Dark Ages lasted for several 100 million years, a long pause in the cosmic story. During this time, the temperature of the cosmic microwave background continued to drop, and the wavelengths of its photons stretched. The universe expanded by many orders of magnitude, and the gas density decreased. Yet the gravitational potential wells grew deeper as they accumulated mass. The fluctuations seeded by inflation continued to grow under gravity's influence, amplifying contrasts in density. Although no stars illuminated the cosmos, other processes were at work. Dark matter halos merged, creating turbulence and heating in the gas. Shock waves formed as gas fell into growing potential wells. These shocks could trigger the formation of molecular hydrogen, enabling cooling. Meanwhile, chemical reactions in the gas produced trace amounts of molecules, such as helium hydride, the universe's first molecular compound. These processes quietly prepared the medium for the first spark of stellar fusion. Despite the name Dark Ages, the universe was not entirely dark at all wavelengths. Photons of the microwave background still bathed space in a faint glow. The temperature of this radiation provided the thermal bath for gas and influenced the cooling rates. In addition, high-energy processes, such as annihilation of dark matter particles, if they occur, could produce photons. These subtle sources remind us that even in darkness, the universe was active. Eventually, the densest halos reached the critical conditions to ignite nuclear fusion. When hydrogen nuclei fused into helium within the cores of these protostellar clouds, enormous amounts of energy were released. The first stars burst into existence, flooding the cosmos with ultraviolet radiation. This radiation split apart neutral hydrogen atoms, reionizing the intergalactic medium. The universe transitioned from darkness to light, and the cosmic dawn began. But that is a tale for another part of our journey. The awakening of starlight marked the end of our journey through the Dark Ages. With it came new chapters in the cosmic story: the formation of galaxies, the coalescence of clusters, the synthesis of heavier elements, and eventually the emergence of life. Yet the foundations for all of these later events were laid in the epochs we have explored: the birth of time and space, the amplification of tiny fluctuations during inflation, the forging of the first nuclei, the release of the cosmic microwave background, and the quiet assembly of structure in the dark. Reflecting on these early times invites a sense of wonder. From a state with no space and no time, a universe emerged that evolved complexity and beauty. Minute quantum ripples became galaxies and clusters. The afterglow of a hot plasma became a cold, uniform background that we can observe. The silence of the Dark Ages set the stage for the first stars, whose light would begin to paint the universe in new colors. The story continues beyond this point, but the themes of transformation, emergence, and growth are already evident. Even as we contemplate the known stages of the early universe, we are reminded of mysteries that remain unsolved. The mechanism behind inflation is still unknown. We assign names like inflaton to the field that drove it, but we do not know its nature. The process that generated the slight excess of matter over antimatter is not fully understood, though theories such as baryogenesis and leptogenesis provide clues. The identity of dark matter, the invisible substance that shaped the cosmic web, eludes detection. Each unanswered question invites curiosity and hints at deeper physics yet to be revealed. Understanding the Planck epoch, when quantum mechanics and gravity were intertwined, might require a theory of quantum gravity. Candidates like string theory and loop quantum gravity attempt to unify these realms, proposing that fundamental particles are excitations of tiny strings, or that spacetime is made of discrete loops. In these theories, singularities may be avoided, with the universe undergoing a bounce or emerging from a higher dimensional state. While these ideas are speculative, they illustrate the depth of our quest to understand the true beginning. The unification of forces in the early universe underscores a recurring pattern in physics. Simple laws give rise to diverse phenomena through symmetry breaking. Just as water freezes into ice with crystal structures, the unified forces cooled into the four interactions we know. The Higgs mechanism, which gives mass to particles, is a type of symmetry breaking. Similarly, the strong force emerged from grand unification and later confined quarks into hadrons. The universe we experience is the outcome of these hidden symmetries and their breaking. Examining the era when quarks roamed freely helps us appreciate the physics of quark-gluon plasma, which scientists recreate for brief moments in particle accelerators. When heavy ions collide at near light speed, they generate temperatures reminiscent of the early universe. In these collisions, quarks and gluons are liberated before quickly recombining. Studying this plasma reveals how the strong force behaves under extreme conditions and informs our understanding of the early seconds after the beginning. The electroweak phase transition, when the electromagnetic and weak forces separated, is another focus of research. The Higgs field, acquiring a non-zero value, gave particles mass. But the nature of this transition could have been first order, second order, or a crossover. If it were first order, bubbles of the new phase would have nucleated and expanded, potentially generating gravitational waves. Future detectors might detect a background of gravitational waves from such early phase transitions, providing a new window into this epoch. The slight asymmetry between matter and antimatter might originate from interactions involving heavy neutrinos. Leptogenesis models propose that the decay of these particles created a surplus of leptons over antileptons, which was then converted into a baryon asymmetry by electroweak processes. Such scenarios require neutrinos to have masses and to be their own antiparticles, known as Majorana particles. Detecting neutrinoless double beta decay would support this idea and link neutrino physics to the cosmic origin of matter. Another relic from the early universe is the cosmic neutrino background. Although these neutrinos are cooler and less energetic than those produced in stars, they outnumber photons by a factor of about 10. They influence the expansion rate of the universe and the growth of structures, leaving subtle imprints in the cosmic microwave background. Advanced experiments aim to detect them indirectly through their effect on beta decays or through coherent neutrino scattering, but a direct detection remains a formidable challenge. Dark matter is central to the formation of structures, but remains unseen except through its gravitational effects. Several particle candidates have been proposed, including weakly interacting massive particles, axions, and sterile neutrinos. Direct detection experiments attempt to observe the rare interactions of dark matter with ordinary matter, while collider experiments look for its production. Observations of dwarf galaxies, galaxy clusters, and gravitational lensing provide constraints on its properties. Understanding dark matter is vital because its nature affects how structures grew in the Dark Ages. The process of baryogenesis requires conditions known as the Sakharov conditions. Baryon number violation, C and CP violation, and departure from thermal equilibrium. In the early universe, the necessary conditions could have been satisfied during grand unification or electroweak phase transitions. The ongoing search for CP violation beyond that, observed in quark decays, may reveal the mechanism behind the asymmetry. Experiments measuring the electric dipole moment of neutrons and electrons, as well as neutrino oscillation studies, aim to uncover new sources of CP violation. While the universe was dominated by radiation for hundreds of thousands of years, the energy density in matter was steadily increasing relative to radiation due to the different scaling laws with expansion. Radiation energy density decreases faster because the energy of photons is redshifted, while matter density decreases only due to dilution. Eventually, the universe became matter-dominated. This transition from radiation to matter domination allowed gravitational collapse to become more effective, enabling structures to grow during the Dark Ages. The cosmic scale factor describes how distances expand with time. During radiation domination, the scale factor increased as the square root of time. During matter domination, it increased as the 2/3 power of time. These relations come from solving Einstein's equations for a homogeneous and isotropic universe. Knowing the expansion history helps us relate physical processes to cosmic timescales, allowing us to reconstruct when recombination occurred and when the first stars could have formed. General relativity, proposed by Albert Einstein, underpins our understanding of cosmic expansion. According to this theory, mass and energy tell spacetime how to curve, and curvature tells matter how to move. The dynamic evolution of the scale factor arises from the Friedmann equations, which link the expansion rate to the energy content of the universe. Within this framework, different components, radiation, matter, and dark energy, control the expansion at different epochs. Early on, radiation dominated. Later, matter took over. And today, dark energy drives acceleration. Although dark energy plays little role in the early universe, its existence raises questions about the ultimate fate of the cosmos. If dark energy remains constant, the expansion will accelerate indefinitely. If it changes, the future may hold surprises. Some models propose a future phase transition, akin to inflation, that could alter the nature of space. Others envision a slow fading of structure as galaxies drift apart. While these scenarios lie far beyond the Dark Ages, pondering them enriches our appreciation of cosmic history. During the photon epoch, the physics of sound waves in the plasma created features known as baryon acoustic oscillations. These oscillations left not only imprints in the cosmic microwave background, but also in the distribution of galaxies. As the universe transitioned to matter domination, these sound waves froze, leaving a preferred scale in the clustering of galaxies. Measuring this scale provides a standard ruler for cosmology, helping to determine the expansion history and the nature of dark energy. Another subtle imprint from the early universe comes from primordial magnetic fields. If magnetic fields were generated during inflation or phase transitions, they could have influenced structure formation and galaxy evolution. Observations of intergalactic magnetic fields provide hints of such primordial origins. However, their detection and characterization remain challenging. Understanding their origins would add yet another layer to the tapestry of early cosmic physics. The relationship between time and temperature in the early universe can be illustrated through a cosmic timeline. At a fraction of a second after the beginning, the temperature was trillions of degrees, and matter existed as a quark-gluon plasma. Within minutes, the temperature dropped to billions of degrees, allowing nucleosynthesis to proceed. Hundreds of thousands of years later, the temperature was thousands of degrees, enabling recombination. By the time the first stars formed, the cosmic temperature had fallen to a few tens of Kelvin, a cold environment by stellar standards. This rapid cooling was driven by expansion, which converts the energy of particles into the energy of spacetime. As wavelengths stretch, photon energy decreases and the temperature drops. The cooling also allowed different processes to freeze out as reaction rates slowed compared to the expansion rate. The interplay between microphysical reaction timescales and cosmic expansion set the timing of epochs such as neutrino decoupling, nucleosynthesis, and recombination. In the aftermath of inflation, the universe went through a phase known as reheating or preheating. The energy stored in the inflaton field was converted into a hot bath of particles. Reheating could have been violent, with oscillations of the inflaton field decaying into particles at an explosive rate. The details of this process are important because they determine the initial conditions for subsequent evolution. The temperature after reheating sets the stage for baryogenesis, nucleosynthesis, and the formation of the cosmic microwave background. The notion of cosmic dark ages conjures images of stillness, but this period was full of quiet activity. Chemical reactions produced the first molecules. Gravity sculpted the cosmic web. Neutrinos and dark matter streamed through space, largely unhindered. The universe's background radiation cooled and stretched. This interplay of processes created conditions for a spectacular transition when the first luminous sources ignited. To detect signals from the dark ages, astronomers look for radio emission and absorption from the 21 centimeter line of neutral hydrogen. When a region of gas is cooler than the cosmic microwave background, it absorbs photons at this wavelength. When it is warmer, it emits. By mapping this signal across different frequencies, we can reconstruct the three-dimensional structure of the early universe. This technique, known as 21 centimeter tomography, promises to unveil the dark ages as no other method can. Building instruments sensitive enough to map the 21 centimeter signal requires overcoming formidable challenges. The signal is weak compared to human-made radio noise and to emissions from our own galaxy. Calibration and foreground subtraction are critical. Arrays like the hydrogen epoch of reionization array and the square kilometer array are being designed to meet these challenges. If successful, they will open a new window onto a time previously shrouded in darkness. Simulations of the first stars and galaxies are crucial for interpreting these observations. By modeling the physics of gas cooling, star formation, and feedback in dark matter halos, researchers predict the luminosity and spectra of the earliest objects. These simulations inform the design of telescopes, like the James Webb Space Telescope, which aims to observe the first galaxies directly. Together, observations and simulations will reveal how the universe emerged from the Dark Ages. Some theories propose the existence of warm dark matter instead of cold dark matter. In warm dark matter models, the particles have velocities high enough to smooth out small-scale structures. This would delay the formation of the smallest halos and lead to differences in the pattern of galaxy formation. Observations of the Lyman alpha forest, the distribution of dwarf galaxies, and the cosmic web can test these models, providing constraints on the mass and nature of dark matter particles. The possibility of dark matter interacting weakly but not being completely cold leads to a spectrum of models between cold and warm. Self-interacting dark matter models, for instance, propose that dark matter particles scatter off each other. This could reduce the density in the centers of halos and alleviate tensions between observations and simulations. The early universe provides a laboratory for testing these ideas, because dark matter's properties influence how structures form during the Dark Ages. Another line of investigation focuses on axions, hypothetical particles that arise in theories designed to solve the strong CP problem. If axions exist, they could be produced in abundance during the early universe and behave as cold, dark matter. Experimental efforts search for axions through their conversion into photons in strong magnetic fields. Such particles could also affect the cooling of stars and supernovae. Detecting or constraining axions would have profound implications for both cosmology and particle physics. As the first stars formed, they likely produced not only light, but also gravitational waves through core collapse supernovae and binary interactions. Although these signals are weak, a stochastic background of gravitational waves from early stars and black holes might be detectable by future observatories. Gravitational waves, ripples in spacetime predicted by general relativity, provide a way to probe the universe independent of light. They carry information about motions of mass and energy that are otherwise invisible. Cosmic strings are hypothetical, topological defects that could have formed during symmetry-breaking phase transitions. These one-dimensional objects would stretch across space, potentially generating gravitational waves and lensing effects. If they exist, cosmic strings could have influenced structure formation by seeding density perturbations. Searches for gravitational wave bursts and specific patterns in the cosmic microwave background aim to detect or constrain their presence. The thermodynamics of the early universe reveals how entropy increased as the cosmos expanded and cooled. The second law of thermodynamics dictates that disorder tends to increase. As radiation filled a growing volume, the number of accessible states multiplied. Phase transitions, particle decays, and annihilations increased entropy. However, on smaller scales, gravity allowed structure to form, creating pockets of order amid the larger trend of increasing disorder. This tension between entropy and structure is at the heart of cosmic evolution. At the heart of the cosmic narrative is the arrow of time, the sense in which the past differs from the future. The arrow arises from the growth of entropy and is evident in the expansion of the universe. In the early universe, conditions were extraordinarily uniform and low in gravitational entropy. As the cosmos expanded, gravitational instabilities amplified irregularities, leading to the complexity we see today. The arrow of time thus emerges from the interplay of fundamental laws and initial conditions. Another aspect of the early universe is the formation of the first black holes. These could arise from the collapse of massive stars, or from direct collapse of dense gas clouds in early halos. Primordial black holes might have formed directly from density fluctuations in the first moments. Such black holes could contribute to dark matter or seed supermassive black holes observed in galaxies today. The early conditions determine their abundance and mass spectrum, which in turn influence the growth of galaxies. As the first luminous objects formed, they generated feedback that influenced their surroundings. Ultraviolet radiation heated an ionized gas, preventing further collapse in some regions. Supernova explosions injected energy and enriched the interstellar medium with heavy elements. Stellar winds carved out cavities. These feedback processes determined the efficiency of star formation and regulated the pace at which the universe lit up. Understanding these processes requires detailed simulations and observations across wavelengths. One of the earliest molecules formed in the universe was helium hydride, a combination of helium and hydrogen. This molecule forms when helium ions combine with hydrogen atoms and played a role in early cooling processes. Only recently has helium hydride been detected in a planetary nebula, confirming its existence in nature. Its presence in the early universe highlights the simple yet rich chemistry that preceded the formation of complex molecules. The interplay between microphysics and cosmology is evident in these narratives. The properties of elementary particles, such as their masses and interaction strengths, shape the evolution of the universe on the largest scales. Conversely, astronomical observations provide constraints on particle physics, ruling out or favoring certain models. The early universe serves as both a particle accelerator and a cosmic laboratory, bridging the smallest and largest scales of nature. Though we have constructed detailed models of the early universe, there remain observational gaps. We have yet to directly observe the cosmic neutrino background. We have not measured the polarization B modes produced by primordial gravitational waves. The 21-centimeter signal of the Dark Ages remains elusive. Filling these gaps will require innovative instrumentation, creative analysis, and patience. Each new detection will bring us closer to a complete picture of our cosmic origins. In contemplating these early epochs, we also confront philosophical questions. Why does anything exist at all? What determines the laws of physics? Are there multiple universes with different properties? Inflation, with its potential to spawn a multiverse, invites speculation about realms beyond our own. While such ideas may never be testable, they stimulate inquiry and broaden our perspective. They remind us that the universe we inhabit may be one of many possibilities. Our understanding of the early universe has grown tremendously over the past century. From the recognition of cosmic expansion to the precision measurements of the cosmic microwave background, each discovery has refined our picture. Yet each answer opens new questions. The quest to understand the first moments continues to drive theoretical work and inspire new experiments. It is a testament to human curiosity and our desire to know where we come from. In the darkness before the first stars, the universe was simple in composition, but rich in potential. Hydrogen and helium dominated, with trace amounts of deuterium and lithium. There were no rocky planets, no complex molecules, no biological life, yet contained within that simplicity were all the ingredients for future complexity. The elements forged in later stars would build planets, and life would emerge to ponder its origins. All of this potential was present, even when the cosmos was dark and quiet. The slow pace of change during the Dark Ages contrasts with the rapid transitions that preceded it. Inflation occurred in a fraction of a second. Nucleosynthesis lasted minutes. Recombination lasted thousands of years. But the Dark Ages spanned hundreds of millions of years. This long interval allowed gravity to work gradually, assembling the structures that would later light up. It also allowed the cosmic microwave background to cool and lose energy, making the temperature differences we measure today subtle yet informative. As we look out into space, we look back in time. Because light travels at finite speed, distant objects show us earlier epochs. Observing galaxies at redshifts of 10 or more reveals glimpses of the cosmic dawn. Detecting the 21-centimeter signal from the Dark Ages will let us see structures even before the first stars. Observing the cosmic microwave background lets us peer back to the time of recombination. In this way, the universe provides its own archaeological record. The interplay between light and matter is central to our ability to observe the cosmos. Photons carry information across vast distances. During the Dark Ages, when there were no luminous sources, the cosmic microwave background remained the only pervasive light. Later, starlight and quasar light illuminated the fog, and their photons brought information to us after billions of years. Each stage of cosmic history has its own messengers, whether photons, neutrinos, cosmic rays, or gravitational waves. Deepening our understanding of the early universe also informs our understanding of fundamental constants. The fine structure constant, which measures the strength of electromagnetic interactions, and the masses of quarks and leptons influence nucleosynthesis and cosmic microwave background anisotropies. Observations constrain how much these constants could vary over cosmic time. Thus far, evidence suggests they have remained remarkably constant, reinforcing our confidence in using early universe physics to test fundamental theories. The interplay between theory and observation is a hallmark of cosmology. Theories of inflation predicted specific patterns in the cosmic microwave background that were later observed. Models of nucleosynthesis predicted helium and deuterium abundances that match measurements. Predictions of dark matter's influence on structure have been borne out by galaxy surveys. At the same time, observations of accelerated expansion forced theorists to introduce dark energy. This dialogue between thought and evidence continues to refine our understanding. Within the Dark Ages, there may have been rare luminous transients, such as primordial black hole accretion events or annihilation of dark matter in dense regions. These events could have produced brief flashes of high-energy radiation. While such phenomena would be difficult to detect today, they add richness to the otherwise dark landscape. They remind us that even in periods of apparent stillness, the universe might harbor surprises. As we trace the timeline from the first instant to the first stars, we appreciate the delicate balance required for complexity to emerge. Slight changes in fundamental parameters could have prevented inflation, nucleosynthesis, or star formation. If the baryon asymmetry were different, there might be no matter. If the cosmic microwave background fluctuations were larger, galaxies might have collapsed too quickly. If smaller, structures might never have formed. The universe seems finely tuned in ways that are still being explored. It is also important to recognize that our narrative is a synthesis of many pieces of evidence. Each observation, abundances of light elements, cosmic microwave background anisotropies, large-scale structure surveys, provides a window onto different epochs. By combining these windows, we reconstruct a cohesive story. Yet we must remain open to the possibility that new data could alter parts of the tale. Science is a continuous process of refinement, and the early universe is no exception. Looking ahead, future missions and instruments promise to fill gaps in our knowledge. The James Webb Space Telescope will observe the first galaxies and perhaps the first stars. Radio arrays will map the 21-centimeter signal across cosmic time. Gravitational wave detectors may capture whispers of primordial waves. Laboratory experiments will search for dark matter and measure neutrino properties. Each of these efforts extends our ability to test and enrich the story of the cosmic dawn. The story of our origins thus stretches from the smallest scales of quantum fluctuations to the largest scales of cosmic structure. It connects the behavior of subatomic particles with the formation of galaxies. It reveals how physical laws operating at unimaginable energies shaped the universe we inhabit. It invites us to view ourselves as part of a grand tapestry woven over billions of years from the threads of time, space, energy, and matter. Among the observable signatures of the early universe, subtle distortions in the spectrum of the cosmic microwave background could arise from energy release after recombination, processes such as the decay or annihilation of dark matter particles, the dissipation of small-scale acoustic waves, or the formation of primordial black holes could inject energy into the cosmic plasma. This energy would slightly alter the blackbody spectrum, creating what are called mu and Y distortions. Detecting these spectral distortions would open a new avenue to probe physics beyond the standard model and to measure primordial fluctuations on scales not accessible through anisotropies alone. Measuring the cosmic microwave background with enough precision to detect spectral distortions requires instruments with exquisite sensitivity. Proposed missions, like the Primordial Inflation Explorer and the Spectrophotometer for the History of the Universe, Epoch of Rayonization, and ICES Explore, aim to achieve this. They will measure the absolute spectrum of the background across a wide range of frequencies. If they find distortions, we would gain insights into the dissipation of acoustic waves and the possible decay of particles in the early universe. Another frontier is the detection of primordial gravitational waves. These waves could be generated during inflation, carrying information about the energy scale and dynamics of inflation. They would imprint a unique B-mode polarization pattern on the cosmic microwave background. Current experiments have not yet detected primordial B modes, but limits are improving. Space-based observatories like LightBird and ground-based arrays like the Simons Observatory and CMBS-4 aim to measure polarization with unprecedented sensitivity. A detection would provide a direct window into the physics of inflation. The cosmic horizon defines the boundary beyond which light has not had time to reach us since the beginning. This horizon grows as time passes and signals travel. But because the universe is expanding, regions currently beyond the horizon may never become observable. The cosmic horizon therefore limits our knowledge to a finite region of the universe. Inflation implies that the unobservable region is vast compared to what we can see, potentially containing different structures or even different physical conditions. This realization humbles us, reminding us that our cosmic neighborhood may be only a small patch of a much larger reality. We often think of the universe as a sphere expanding into something, but it is more accurate to say that space itself expands everywhere, stretching the distances between commoving points. There is no center of the expansion. Every point sees the universe expanding away from it. The expansion is described by the metric expansion of space, a key concept in general relativity. Galaxies recede from one another not because they are moving through space like projectiles, but because the space between them is growing. During inflation, this expansion was so rapid that it dwarfed any speed of motion. Inflation also predicts that the universe is spatially flat to a high degree. Observations of the cosmic microwave background confirm this, with deviations from flatness limited to less than 1%. A flat universe implies that parallel lines remain parallel on cosmological scales, and that the sum of angles in a large triangle equals 180 degrees. In such a universe, the total energy density is equal to the critical density. If the density were lower, space would be negatively curved. If higher, positively curved. The flatness of space is a clue to the behavior of inflation and the total energy content of the cosmos. The composition of the universe at the time of recombination influences the height and position of acoustic peaks in the microwave background. Baryon density affects the amplitude of odd and even peaks because baryons enhance compression in the plasma. Dark matter density influences the overall shape of the power spectrum and the growth of perturbations. The effective number of neutrino species alters the expansion rate, shifting the time of matter radiation equality. By fitting models to the data, cosmologists extract these parameters with remarkable precision. The helium abundance measured today not only confirms predictions of Big Bang nucleosynthesis, but also places limits on the number of light particle species. If there were additional light particles beyond the 3 known neutrino flavors, they would change the expansion rate during nucleosynthesis and recombination. Observations of helium and deuterium, combined with cosmic microwave background data, constrain any additional species. These constraints inform theories that extend the standard model, such as those predicting sterile neutrinos or axion-like particles. In the context of the early universe, it is instructive to compare the sizes of the cosmological horizon at different times. At the time of recombination, the horizon encompassed regions that today span about a degree across the sky. Each patch of the sky at that scale was causally connected at recombination. Inflation expanded a tiny patch of pre-inflationary space into the entire observable universe, explaining why these patches share the same conditions. The sizes of these horizons are encoded in the pattern of anisotropies we observe. The interplay between cosmic expansion and light also gives rise to redshift. As space expands, the wavelength of a photon stretches, causing its frequency to decrease and its energy to diminish. The redshift we observe in the light from distant galaxies tells us how much the universe has expanded since that light was emitted. The redshift of the cosmic microwave background is about 1,100, meaning the universe has expanded by a factor of about 1,000 since recombination. Redshift is the cosmic clock that allows us to translate distances into times. While the early universe was homogeneous and isotropic on large scales, it contained fascinating phenomena on small scales. Topological defects like cosmic strings or domain walls could have formed during phase transitions and left imprints on the cosmic microwave background. Such features have not been observed yet, but their absence constrains models of symmetry breaking. Similarly, primordial black holes, if they existed, would produce unique gravitational lensing signatures and could contribute to dark matter. Their existence remains speculative, but intriguing. The cosmic microwave background not only tells us about conditions at recombination, but also about what happened along the line of sight between us and that epoch. Photons can be scattered by free electrons during reionization, producing additional polarization. They can be deflected by gravitational potentials, a phenomenon known as weak lensing, which smooths the anisotropy pattern on small scales. They can be absorbed or scattered by dust in our own galaxy. Careful analysis of these secondary effects allows cosmologists to reconstruct the distribution of matter between us and the last scattering surface. In addition to the main temperature fluctuations, there are secondary anisotropies in the cosmic microwave background. The Sunyaev-Zeldovich effect occurs when CMB photons scatter off hot electrons in galaxy clusters, distorting their spectrum. The integrated Sachs-Wolf effect arises when photons traverse time-varying gravitational potentials, gaining or losing energy. These effects provide information about galaxy clusters, dark energy, and the growth of structures. Thus, even the interactions of photons, long after recombination, reveal details about the universe. On Earth, we can study remnants of the early universe through meteoritic samples and isotopic ratios. Some isotopes, such as lithium-7 and deuterium, preserve signatures of bigbang nucleosynthesis. Their abundances in primitive meteorites and in the atmospheres of ancient stars provide direct tests of nucleosynthesis predictions. The discrepancy between predicted and observed lithium abundances challenges our understanding and prompts new models or better measurements. These chemical fossils complement the cosmic microwave background as evidence of the early universe. Looking at the cosmic web, we see an intricate network of filaments, clusters, and voids. This pattern is not random, but reflects the initial fluctuations amplified by gravity. Simulations, starting from tiny variations measured in the cosmic microwave background, reproduce the large-scale structure we observe today. They show how dark matter halos merge, how gas cools and forms stars, and how feedback processes shape galaxies. The success of these simulations in matching observations supports the standard cosmological model, which includes a dark age period before star formation. Ultimately, the story of the early universe is not only about physics and cosmology, but also about perspective. Standing on a small planet orbiting an ordinary star, we are able to reconstruct events that occurred billions of years ago at energies and densities far beyond our daily experience. Through ingenuity, we build instruments that detect faint whispers of cosmic history. Through imagination, we interpret those whispers and weave them into a narrative. The calm and slightly mysterious tone that accompanies such reflection mirrors the majesty of the universe itself. As our instruments grow more sensitive, we begin to detect signals that were previously beyond reach. One such signal is the global 21 centimeter absorption feature, which may arise when the first stars turned on. Early observations have hinted at an unexpectedly deep absorption, suggesting that the gas was cooler than expected, or that the background radiation was enhanced. While these findings are still debated, they highlight the potential surprises awaiting us. A deeper than expected 21 centimeter signal could hint at interactions between dark matter and baryons, or new astrophysical processes during cosmic dawn. Another area of active research involves the precise measurement of the baryon density. Bigbang nucleosynthesis and cosmic microwave background analyses provide independent estimates of the baryon to photon ratio. Comparing these estimates serves as a consistency check and can reveal new physics. Additionally, baryon acoustic oscillations measured in the distribution of galaxies offer a third way to estimate baryon density. The concordance among these methods strengthens the standard cosmological model, but any discrepancy could point toward unknown components or interactions. The detection of cosmic neutrinos remains an audacious goal. One proposed method involves capturing relic neutrinos in heavy nuclei via neutrino capture reactions, which would produce an electron without the usual kinematic threshold. Experiments like Ptolemy plan to use tritium targets to detect such events. Although the expected rate is extremely low, the ability to directly detect the cosmic neutrino background would be a triumph, confirming a prediction of the Big Bang and measuring the neutrino mass scale. The early universe also sets the stage for cosmic ray physics. High-energy particles, including protons and nuclei, traverse the universe and occasionally strike Earth's atmosphere. Some of these cosmic rays may originate from the decay of supermassive particles produced in the early universe, or from the evaporation of primordial black holes. While most cosmic rays are accelerated in supernova remnants and active galactic nuclei, searching for exotic sources provides another way to probe high-energy processes that took place soon after the beginning. Chemistry in the early universe was limited, but not trivial. The formation of molecules like hydrogen molecular ions, helium hydride, and later molecular hydrogen involved delicate balance among reactions. These molecules influenced the cooling and collapse of gas in the first halos. As heavy elements were synthesized in the first stars, a richer chemistry emerged, leading eventually to molecules like water, carbon monoxide, and simple organic compounds. The chemical evolution of the cosmos thus began long before planets formed, with roots in the Dark Ages. The cosmic timeline is often visualized as a series of epochs marked by distinct physical processes. Yet these epochs blend into one another, with overlapping timescales. For example, neutrino decoupling and electron, positron annihilation overlap during the first seconds. Nucleosynthesis occurs while neutrinos are streaming away. The photon epoch begins while nucleosynthesis is wrapping up. Recombination overlaps with the tail end of the photon epoch. The Dark Ages gradually transition into rayonization. Recognizing these overlaps helps us appreciate the continuous nature of cosmic evolution. In cosmology, cross-disciplinary techniques are essential. Statistical methods are used to analyze anisotropy maps and galaxy surveys. High-energy physics informs models of inflation and particle production. Astrochemistry guides our understanding of cooling and star formation. Gravitational lensing techniques reveal the distribution of dark matter. Machine learning algorithms help sift through large datasets to find subtle signals. The study of the early universe thus exemplifies the interconnectedness of scientific disciplines, each contributing to a deeper understanding of our origins. The synergy between theory and observation continues to be a driving force. Theories propose mechanisms for inflation, baryogenesis, and dark matter. Observations test these ideas. An observation of primordial gravitational waves would constrain inflation models. A detection of spectral distortions in the cosmic microwave background would inform us about energy dissipation. Non-detection of certain signatures constrains the parameters of models. This feedback loop ensures that our narrative remains anchored to reality while still allowing for imaginative exploration. There is poetry in knowing that every second of every day, relic photons from the hot plasma of the early universe pass through us. They fill the space between stars and planets, bathing Earth in an invisible glow. Their wavelengths have been stretched by cosmic expansion, from visible light to microwave, cooling as the universe cooled. Yet they still carry the memory of a time when matter and light were intertwined. When you warm your hands by a fire, the heat you feel is the same type of radiation, albeit at a different temperature and origin. This connection between the grandest scales and the ordinary warmth we experience is a reminder of our intimate relationship with the cosmos. Similarly, neutrinos from the early universe and from the heart of the sun stream through our bodies by the trillions each second. We do not feel them because their interactions are so weak, yet their presence is constant. The detection of such particles requires massive detectors buried deep underground or under ice, shielded from cosmic rays. These detectors watch for the occasional flash of light produced when a neutrino interacts. Each detection is a message from the distant past or from violent events across the cosmos, captured on Earth by patient instruments. Contemplating the early universe invites us to reflect on the passage of time. The events we have described unfolded over timescales ranging from fractions of a second to hundreds of millions of years. The human experience of time is very different, but we can translate cosmic durations into human terms. Imagine compressing the universe's history into a single year. The Big Bang occurs at midnight on January 1st. Recombination happens on January 5th. The Dark Ages last until early February. The first stars appear mid-February. Our solar system forms in early September. Dinosaurs roam on Christmas Day, and human history occupies the last seconds before midnight on December 31st. Such analogies help us grasp the vastness of cosmic time and our brief place within it. In telling the story of the early universe, we also tell a human story. Our curiosity drives us to look up at the night sky and wonder about our origins. The answers we find in the faint glow of the cosmic microwave background and in the whispers of neutrinos enrich our sense of belonging to the universe. The calm, slightly mysterious tone of this narrative mirrors the wonder we feel when pondering the unknown. Even as we uncover the physics of the first moments, there will always remain questions, inviting us to continue exploring. This journey through the first instance to the first atoms reveals how intimately connected everything is. From the symmetry breaking of fundamental forces to the cooling of cosmic gas, from the emergence of sound waves in plasma to the quiescence of the Dark Ages, each step leads naturally to the next. The universe is a continuous story, without sharp boundaries between epochs, evolving smoothly, yet punctuated by moments of rapid change. Understanding this continuity helps us appreciate the delicate balance that makes existence possible. It invites us to recognize that we are not separate from the cosmic narrative, but participants in its ongoing unfolding. As we conclude this part of the journey, it is worth emphasizing that the early universe is not merely a distant memory, but an ever-present foundation. The photons of the cosmic microwave background continue to cool. The neutrinos continue to stream. The dark matter continues to sculpt. The atoms in our bodies were once forged from hydrogen and helium created in nucleosynthesis, enriched later by stars that themselves trace their lineage to the first luminous objects. The cosmic evolution that began in the first instance continues today in every galaxy, every star, every molecule. Our story is woven from this cosmic fabric, and by studying the early universe we come to understand not only the cosmos, but ourselves. High-energy cosmic rays are another product of stellar explosions. When supernova shockwaves accelerate protons and heavier nuclei to near light speed, these particles stream across interstellar and intergalactic space. They contribute to ionizing the interstellar medium and affect the chemistry of molecular clouds. Studying cosmic rays offers insight into the engines of supernovae and the conditions of the early universe. Quasars are among the brightest objects in the universe, powered by accretion onto supermassive black holes. In the early universe, quasars may have played a significant role in reionizing their surroundings and heating intergalactic gas. Their powerful winds can expel gas from galaxies or compress it, triggering star formation. Observing quasars at high redshift helps us understand how the first massive black holes formed and grew. Dwarf galaxies, though small, are essential players in cosmic evolution. They are numerous and often serve as building blocks that merge to form larger systems. Their shallow gravitational wells make them susceptible to feedback, so a few supernovae can dramatically affect their gas content. Studying nearby dwarf galaxies provides clues about the conditions that prevailed during the cosmic dawn and the role of small halos in reionization. Another important aspect of the cosmic dawn is the formation of the first clusters of galaxies. As dark matter halos merged, they created larger potentials capable of holding on to gas heated by early star formation. These protoclusters were sites of intense activity, with many galaxies forming stars and interacting with each other. Observations of high redshift protoclusters offer a glimpse into the nascent, large-scale structure of the universe. In galaxy clusters, the environment can both suppress and stimulate star formation. The high density of galaxies leads to frequent interactions that disturb gas reservoirs and compress molecular clouds. Shockwaves and tidal forces can ignite bursts of star formation in some cluster members, creating luminous blue arcs. At the same time, the hot intracluster medium strips gas from others, quenching their ability to form stars. Some galaxies experience episodes of star formation so intense that they outshine entire clusters in infrared light. These ultraluminous starburst galaxies rapidly convert gas into new stars, often triggered by mergers or interactions. Dust absorbs the ultraviolet radiation from young stars and re-emits it in the infrared, giving these galaxies their brilliance. Embedded within many of them are growing black holes, adding another layer of complexity to their evolution. Black holes not only shape their host galaxies, but also interact with one another. When galaxies merge, their central black holes sink toward the center and eventually coalesce. The violent union releases gravitational waves, ripples in spacetime, that travel across the universe. Modern observatories detect these waves, providing a new way to study cosmic events invisible to traditional telescopes. Observational astronomy has recently begun to glimpse galaxies from the first few 100 million years after the Big Bang. These faint smudges of light traveled across cosmic time to reach us, carrying information about star formation, gas content, and the production of ultraviolet radiation. Advanced telescopes with large mirrors and sensitive detectors are essential for detecting such distant objects. Each detection pushes our knowledge deeper into the cosmic dawn. To understand the complexity of structure formation, scientists construct detailed numerical simulations of the universe. Starting from initial density fluctuations, these simulations follow the growth of dark matter halos, the condensation of gas, and the formation of stars. Feedback processes, mergers, and cosmic expansion are all included, creating virtual universes that can be compared with observations. Such simulations provide a laboratory for testing theoretical ideas. The period before the first stars formed is known as the cosmic dark ages. During this time, the universe was filled with neutral hydrogen and helium, cooled to only a few tens of degrees above absolute zero. Photons from the cosmic microwave background traveled freely, but there were no sources of new light until stars ignited. When ionization began, ionized bubbles expanded and overlapped, eventually leaving only small pockets of neutral gas. The primordial composition of the universe consisted mostly of hydrogen and helium, with trace amounts of lithium. These elements were forged during the first few minutes after the Big Bang. In stellar cores, hydrogen fused into helium, releasing energy and balancing gravity. Heavier elements were created in later generations of stars and dispersed by supernovae, gradually enriching the cosmic soup. Within galaxies, glowing nebulae reveal regions where stars are being born. Ultraviolet radiation from young stars ionizes surrounding gas, causing it to emit light in characteristic colors. Dense molecular clouds, shielded from this radiation, collapse under their own gravity to form clusters of protostars. Observing nebulae allows astronomers to study the conditions that lead to star formation and the feedback that shapes them. The cosmic microwave background is remarkably uniform, but tiny fluctuations in its temperature encode information about the early universe. These anisotropies reflect density variations that seeded all subsequent structure. Sensitive instruments map these fluctuations across the sky, revealing patterns that match theoretical predictions. The subtle variations offer clues about inflation, neutrinos, and the geometry of space. Galactic ecosystems are complex and dynamic. Gas flows in from the cosmic web, is converted into stars, returned via winds and supernovae, and sometimes consumed by central black holes. The balance between inflow and outflow determines how long a galaxy can sustain star formation. Feedback loops regulate this balance, linking the fate of individual stars to the evolution of the whole system. Each wavelength of light tells a different part of the story of the cosmic dawn. Gamma rays trace the most energetic processes, such as annihilating particles or exploding stars. X-rays illuminate hot gas near black holes, while ultraviolet light reveals young stars and ionized gas. Infrared observations penetrate dust and reach back to the earliest galaxies, and radio waves carry information about neutral hydrogen. Despite progress, many questions about the cosmic dawn remain. Did the first stars form individually or in clusters? How did their radiation escape into the intergalactic medium? Were early supernovae predominantly spherical or collimated into jets that hurled elements into nearby space? Answering these questions requires both observational advances and theoretical insight. Reflecting on these mysteries, we are reminded that science is a journey rather than a destination. Each discovery opens new questions, and each observation deepens our curiosity. Our exploration of the cosmic dawn is not merely an academic exercise. It taps into fundamental questions about origins and interconnectedness. The wonder we feel when contemplating the first light is itself part of the story. Another relic of the early universe is the cosmic neutrino background, a sea of ghostly particles that decoupled from matter within the first second after the Big Bang. These neutrinos carry information about conditions when the universe was less than a billionth as old as it is today. They move almost at the speed of light and barely interact with anything. Detecting them directly is challenging, but their effects can be inferred from cosmological observations. Future observatories promise to revolutionize our view of the cosmic dawn. The square-kilometer array will map the 21-centimeter signal with unprecedented sensitivity. 30-meter-class optical telescopes will resolve individual stars in distant galaxies. Space missions will study the infrared and sub-millimeter sky, extending the reach of current surveys. Each new instrument brings us closer to witnessing the first galaxies ignite. The seeds of cosmic structure were planted during an even earlier epoch, known as inflation. Tiny quantum fluctuations were stretched to macroscopic scales, becoming the density variations that later grew into galaxies. These fluctuations also produced sound waves in the primordial plasma, leaving imprints known as baryon acoustic oscillations. By measuring these patterns today, astronomers can probe the physics of inflation and the composition of the universe. As the universe evolves, its expansion rate is influenced by different energy components. During the cosmic dawn, radiation and matter dominated the energy budget, slowing the expansion and allowing structure to form. In more recent cosmic time, an unknown component dubbed dark energy has begun to accelerate the expansion, stretching the space between galaxies. Understanding how dark energy behaves and when it became dominant remains one of cosmology's biggest challenges. Computational astrophysics is undergoing a revolution driven by advances in algorithms and machine learning. Massive simulations produce terabytes of data, which require sophisticated techniques to analyze. Neural networks help identify patterns in observational data, from gravitational lens candidates to faint high redshift galaxies. The synergy between computation and observation accelerates discovery and brings new insights into the cosmic dawn. The story of the first light inspires creativity beyond science. Artists imagine the glow of primordial stars. Musicians compose pieces evoking the vastness of space, and writers explore themes of beginnings and connections. These creative interpretations translate complex scientific ideas into emotional experiences. Such collaborations enrich both art and science, making the cosmic dawn accessible to a wider audience. The universe lay in silence after the first burst of light faded into the background. In those early ages, there were no stars and no galaxies, only a vast darkness filled with cooling hydrogen gas. The residual glow of the cosmic afterglow lingered as a faint whisper of heat, and tiny density ripples seeded by primordial fluctuations waited patiently. It was a time when matter gathered itself together under gravity, slowly preparing the stage for the first brilliant actors. Within that darkness, slight enhancements in density began to draw gas toward themselves. Clouds of hydrogen and helium collapsed into tighter knots inside invisible halos of dark matter. As the gas compressed, it heated, and internal turbulence and shocks triggered the formation of massive protostars. These first stars were gargantuan compared to those of today, hundreds of times the mass of our Sun, and they shone with ferocious luminosity for only a brief moment in cosmic terms. The first generation of stars, often called Population 3, were born in pristine clouds without any heavy elements. Because they lacked metals to cool them efficiently, they grew to enormous sizes before igniting nuclear fusion in their cores. Their internal temperatures climbed higher than any star we know now, and their surface temperatures blazed hotter than we can imagine. They lived fast and bright, burning their nuclear fuel in a few million years before meeting a dramatic end. These colossal stars marked the end of the cosmic dark ages. They filled their surroundings with harsh ultraviolet light that ionized the neutral hydrogen, making the intergalactic medium transparent again. Their intense radiation carved out bubbles of ionized gas around them, which expanded and eventually overlapped to form large swaths of clear space. As their light reached further into the darkness, the fog of neutral atoms gradually lifted and the universe began to glow. The dawn of stars was the dawn of new possibilities. When their short lives concluded, these early giants exploded as supernovae. Their deaths were not quiet affairs. They tore themselves apart in titanic blasts that sent shockwaves rippling through space. In the infernos of these explosions, lighter elements were forged into heavier ones, like carbon, iron, and zinc, enriching the primordial gas with ingredients for future generations of stars and planets. The material they ejected raced outward at a significant fraction of the speed of light, seeding their environs with metals that would one day form worlds. The pattern of birth and death of these first stars set the tone for cosmic evolution. With each generation, the interstellar medium became slightly more enriched in heavy elements, allowing subsequent stars to form with lower masses and longer lifespans. The heavy elements from early supernovae cooled the gas more effectively, leading to smaller stars similar to those we see today. In this way, the first luminous beacons transformed the chemistry of the universe and opened pathways toward complexity. While these pioneering stars were massive and brief, they still followed the general principles that govern the life cycles of all stars. A star's life begins in a cold, dense cloud of gas known as a nebula, where gravity pulls material inward until a protostar forms. As the protostar contracts, pressure and temperature rise in its core. When the core temperature becomes high enough, around 15 million degrees Celsius, hydrogen atoms begin to fuse into helium, releasing energy that halts the collapse and causes the new star to shine. This moment marks the star's entry onto the main sequence, a long, stable phase during which the outward pressure from nuclear fusion balances the inward pull of gravity. For most of its life, a star converts hydrogen into helium in its core, radiating light and heat into space. The length of time a star spends in the main sequence depends on its mass. More massive stars burn fuel quickly and have shorter lives, while smaller stars burn their fuel slowly and can shine for billions of years. This simple relationship between mass and lifespan shapes the demographics of stars across galaxies. As a star exhausts the hydrogen in its core, the delicate balance between gravity and pressure is disturbed. The core contracts and heats further while the outer layers expand. The star swells into a red giant, its atmosphere cooling and reddening. In this phase, helium fusion begins in the core, creating carbon and oxygen. In low-mass stars like our Sun, this helium-burning phase is relatively gentle. Eventually, low-mass stars can no longer sustain fusion, and their outer layers drift away into space, forming beautiful planetary nebulae. The exposed core becomes a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen. Over billions of years, without new sources of energy, the white dwarf cools and fades, becoming a black dwarf too faint to detect. This quiet end contrasts with the violent deaths of their massive cousins. High-mass stars live intense but brief lives. After fusing hydrogen and helium, their cores reach temperatures and pressures high enough to fuse heavier elements like carbon, oxygen, and silicon. Layer upon layer of fusion shells build up inside the star. When the core becomes mainly iron, fusion no longer releases energy. Iron fusion consumes energy instead. Gravity wins over pressure, and the core collapses catastrophically. The ensuing shock rebounds off the dense core and propels the star's outer layers into space. The explosion of a high-mass star is what we call a supernova. The energy released is so immense that for a brief time, a single supernova can outshine an entire galaxy. The shockwave coursing through the star's outer layers triggers rapid neutron capture, creating elements heavier than iron. These heavy elements, including gold and uranium, are scattered into the cosmos. The stellar core that remains can become a neutron star, an object so dense that atomic nuclei are crushed together, or, if massive enough, collapse further into a black hole. These cataclysmic events are not just spectacular, they are necessary for the cosmic ecosystem. The heavy elements from supernovae enrich the gas clouds that will form new stars and planets, enabling the chemistry required for life. Without the violent deaths of massive stars, the universe would remain a simple place of hydrogen and helium. The cycles of star birth and death gradually transform the cosmic landscape, building complexity from simplicity. The energy released by supernovae also stirs the interstellar medium, sweeping up gas and dust and triggering new waves of star formation. In some regions, shock fronts compress clouds to the point of collapse, igniting yet another generation of stars. Elsewhere, the force of the blast clears out gas and leaves behind voids. In this way, supernova feedback shapes the structure of galaxies and influences how quickly they convert gas into stars. As more stars were born and died, gas and dark matter continued to assemble into larger structures. The universe's matter distribution was not uniform. Gravity pulled material into filaments and nodes, creating a vast cosmic web. Dark matter, invisible yet dominant, provided the scaffolding on which ordinary matter could gather. Gas fell into these dark matter halos, cooled, and formed stars, giving birth to the first galaxies. The earliest galaxies were small and fragile by today's standards. They contained only a fraction of the mass of the Milky Way and were composed mostly of hydrogen and helium. Their gravity struggled to hold onto gas when supernovae exploded, and many of these tiny structures were blown apart. Yet the dark matter halos continued to grow by merging with each other and accreting more mass, creating deeper potential wells that could retain gas despite the disruptive force of stellar explosions. Once these halos became massive enough to hold their gas, they could sustain continuous star formation. A galaxy is, at its simplest, a system of stars bound by gravity that is dominated by dark matter. It can continue forming stars over long periods because it has sufficient mass to keep its gas from escaping. In these first galaxies, feedback from stars and the central black holes modulated the rate of star formation, preventing the entire gas supply from being converted into stars at once. As time progressed, galaxies interacted with one another. They collided and merged, exchanging stars and gas and triggering bursts of star formation. These interactions built up larger galaxies and contributed to the intricate cosmic web of clusters and filaments. The gravitational pull of dark matter guided these dances, while the energy from supernovae and active nuclei regulated the pace. Through countless mergers and interactions, the diverse population of galaxies we observe today gradually emerged. The cosmic web itself is a tapestry woven by gravity. Filaments of dark matter and gas connect nodes where galaxies and clusters reside. Voids, immense regions with very little matter, exist between the filaments. Simulations show that this web-like structure arises naturally from the growth of tiny density fluctuations in the early universe. Over billions of years, matter flows along these filaments toward the nodes, feeding the growth of galaxies and clusters. In these nodes, gas can cool rapidly and form stars efficiently. Over time, clusters of galaxies form as groups of galaxies fall together into common potential wells. Within clusters, galaxies can be stripped of their gas by interactions with the hot intracluster medium, quenching star formation. In the outskirts, galaxies continue to accrete gas from the intergalactic medium, fueling further star birth. The cosmic environment influences each galaxy's evolution, from starbursting dwarfs to massive ellipticals. Central supermassive black holes, which form during the early stages of galaxy assembly, also play a pivotal role. As gas falls toward these black holes, it can heat up and produce energetic jets and winds. These outflows can blow gas away from the galactic center, suppressing star formation, or compress gas in surrounding regions, triggering new stars. The feedback from black holes, thus, couples the fate of galaxies to the growth of their central engines. All these processes unfolded while the universe was undergoing a profound transformation. After recombination, when protons and electrons first combined to form neutral hydrogen, the universe entered an epoch known as the Dark Ages. There were no luminous sources to light up space, and neutral hydrogen dominated the intergalactic medium. Light from that era could travel only a limited distance before being absorbed. The universe remained in this dark state until the first stars and galaxies ignited. Ionization refers to the period when the neutral hydrogen in the intergalactic medium was transformed back into ionized plasma. Energetic, ultraviolet photons emitted by the first stars and galaxies stripped electrons from hydrogen atoms, recreating a diffuse, ionized gas. As more luminous sources formed, the ionized regions around them grew and overlapped. The universe gradually transitioned from mostly neutral to mostly ionized, restoring the transparency that we enjoy today. This transformation was driven by the combined light of many young galaxies. In the timeline of cosmic history, ionization occurred relatively early, between about 150 million and 1 billion years after the Big Bang. During this period, the density of matter decreased as the universe expanded, and the scattering of photons by free electrons became less frequent. Once hydrogen was ionized again, photons could travel freely across vast distances. The end of ionization marks the completion of the cosmic dawn and the beginning of the epoch when galaxies and large-scale structures grew in a fully transparent universe. The process of reionization was not instantaneous. Around each luminous source, a bubble of ionized gas formed and expanded. These bubbles grew as long as the source continued to shine, and they could merge with neighboring bubbles. Meanwhile, recombination of electrons and protons competed with ionization, especially in dense regions. The frontier between ionized and neutral gas moved slowly outward over hundreds of millions of years. Observations of distant quasars provide important clues about when reionization ended. The spectra of quasars contain absorption features caused by intervening hydrogen gas. At certain redshifts, quasars show broad troughs where the light has been absorbed by neutral hydrogen, indicating that the gas was not yet fully ionized. Quasars seen at slightly lower redshifts show clearer spectra, suggesting that reionization was largely complete by the time their light set out. These observations, combined with measurements of the cosmic microwave background, help constrain the timeline of this critical epoch. Astronomers also study the reionization era by looking for the faint signals of neutral hydrogen using radio telescopes. The 21-centimeter emission line of hydrogen is redshifted to long wavelengths by the expansion of the universe. Detecting this weak signal will allow us to map the distribution of neutral and ionized gas during the cosmic dawn. New instruments and surveys are being developed to measure this signature, promising to reveal the detailed progression of reionization and the properties of the early galaxies that drove it. Reionization fundamentally changed the thermal state of the intergalactic medium. The gas heated up as it was ionized, increasing the pressure and inhibiting the collapse of smaller halos. This heating may have suppressed the formation of some dwarf galaxies by preventing their gas from cooling. At the same time, larger halos were relatively unaffected and continued to form stars. Thus, reionization not only illuminated the universe, but also influenced the subsequent formation of structures. The first galaxies responsible for reionization were likely small and numerous. Each one contributed a modest fraction of the ionizing photons, but collectively, they overwhelmed the neutral hydrogen. Their ultraviolet radiation leaked into the intergalactic medium through channels created by supernova explosions and stellar winds. Dust and heavy elements were scarce, so more of the energetic light could escape. As later generations of stars formed, dust built up and limited the escape of ionizing radiation, marking the end of the era when galaxies could easily reionize their surroundings. Reionization is a topic that continues to be explored by astronomers, and our understanding is still evolving. Observations from the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories are pushing the frontier of our knowledge back toward the first billion years. Each new detection of a distant galaxy or a subtle signature in the cosmic microwave background sheds light on this mysterious time. The cosmic dawn remains a frontier where observations and theory meet to decode the universe's early history. As the universe emerged from reionization, the transparency of space allowed light to travel unimpeded over vast distances. Galaxies could now see each other's light, and their mutual gravitational influences became more pronounced. The cosmic web continued to evolve, with filaments feeding gas into galaxies and clusters. The interplay between dark matter gravity, gas physics, star formation, and feedback shaped the diversity of cosmic structures. In the following epochs, galaxies grew through accretion and mergers. Disk galaxies formed from rotating gas that cooled and settled into thin, rotating structures. Spiral arms developed as density waves propagated through these disks, organizing stars and gas into graceful patterns. Massive elliptical galaxies resulted from major mergers that scrambled the ordered motion of stars. Dwarf galaxies orbited larger systems, sometimes being torn apart by tidal forces. At smaller scales, star formation proceeded in molecular clouds within galaxies. Turbulent motions within clouds created pockets of high density where stars could form. The birth of new stars was influenced by magnetic fields, cosmic rays, and the presence of existing stars. Feedback from young stars, such as stellar winds and radiation pressure, regulated the rate of star formation by dispersing surrounding gas. This self-regulation kept galaxies from converting their gas into stars too quickly. The heavy elements produced by supernovae enriched the interstellar medium, enabling the formation of planets. Dust grains formed in the outer layers of giant stars, and in supernova, ejecta provided the raw materials for planetesimals. Over time, these grains collided and stuck together, forming larger bodies that eventually grew into planets. The presence of heavier elements also allowed for more complex chemistry, setting the stage for the eventual emergence of life. Throughout cosmic history, black holes have been both mysterious and influential. The first black holes may have formed from the collapse of massive population 3 stars, or from direct collapse of gas in the early universe. Over time, as galaxies merged, their central black holes likely merged as well, growing into the supermassive black holes we observe in galactic centers today. These giants feed on surrounding gas, releasing enormous amounts of energy, and sometimes launching jets that can extend far beyond their host galaxies. The energy output of active galactic nuclei, powered by accreting black holes, can regulate star formation on a galactic scale. Jets and winds from the central engine can heat or expel gas, quenching star formation in the host galaxy. In some cases, these outflows may trigger star formation in other regions by compressing gas. The dynamic relationship between a galaxy and its central black hole is an ongoing dance that shapes both partners over cosmic time. As galaxies evolved, they also gave rise to larger structures, such as galaxy groups and clusters. In galaxy clusters, thousands of galaxies are bound together by gravity and immersed in a hot, X-ray emitting plasma called the intracluster medium. Interactions between galaxies in clusters can strip gas from their disks and transform their morphologies. Cluster mergers and accretion from surrounding filaments continue to drive the growth of these immense structures. The cosmic web persists today, its filaments visible in the distribution of galaxies across the sky. Large surveys of galaxies have mapped the positions of millions of galaxies, revealing the intricate patterns predicted by cosmological simulations. The alignment of galaxies along filaments and the presence of voids provide clues about the underlying dark matter distribution. By studying these patterns, astronomers can infer properties of the universe, such as the amount of dark matter and dark energy. Looking back to the epoch of the first stars and galaxies allows us to understand how all of these structures began. The simple initial conditions of the early universe, uniform expansion with tiny density fluctuations, gave rise to a vast diversity of cosmic environments. From the blazing lives of population 3 stars to the cool glow of dwarf galaxies, the journey from simplicity to complexity is a central theme in cosmology. Each step along the way was influenced by the interplay of fundamental forces and the properties of matter. The formation of the first heavy elements in early supernovae not only enriched space, but also influenced the cooling of gas. Metals radiate energy more efficiently than hydrogen and helium, allowing gas to cool to lower temperatures and fragment into smaller clumps. This change in cooling properties led to the formation of lower mass stars and a different stellar initial mass function. Consequently, later generations of stars had longer lifespans and provided more stable radiation fields, influencing the chemical evolution of galaxies. In addition to supernovae, smaller explosions called novae and stellar winds from evolved stars contributed to enriching the interstellar medium. These processes release lighter elements and dust, complementing the heavier elements produced in supernova. The continuous recycling of material through stars and the interstellar medium created a complex chemical milieu in which molecules could form. This molecular richness is a prerequisite for the formation of complex organic compounds. The cosmic dawn also saw the formation of the first black holes. Some may have been the remnants of massive population 3 stars that collapsed directly into black holes. Others could have formed through direct collapse of primordial gas clouds that avoided fragmentation. These seed black holes may have grown quickly by accreting gas and merging with other black holes, becoming the heavyweights that we see at the centers of galaxies today. Their growth was closely tied to the availability of gas and the dynamics of their host galaxies. As the universe expanded, the average density of matter decreased. Cooling times in gas increased, and star formation became less efficient in the diffuse intergalactic medium. At the same time, within galaxies, dense molecular clouds remained fertile sites for star birth. The contrast between low-density voids and high-density galactic cores became more pronounced. This differentiation created a layered universe, where activity is concentrated in certain regions, while others remain relatively quiet. The interplay between gravity and pressure is a recurring theme in cosmic evolution. Gravity pulls matter together, while pressure, from thermal energy or radiation, pushes it apart. In the early universe, radiation pressure was dominant, preventing gas from collapsing. As the universe cooled and expanded, gravity took over in regions with slight density enhancements. This tug-of-war continues in star formation, galaxy evolution, and the dynamics of clusters. Understanding the formation of the first galaxies also involves considering the role of turbulence and magnetic fields. Gas motions within halos can generate turbulence that influences how gas fragments and forms stars. Magnetic fields, though weak, can also affect the collapse of gas and the launching of outflows. These additional factors introduce complexity into models of early galaxy formation and continue to be areas of active research. Feedback from the earliest stars shaped their host halos. The intense radiation and supernova blasts expelled gas from small halos, delaying further star formation. Once halos grew large enough to retain their gas, star formation could proceed more steadily. The timing of when halos crossed this threshold influenced the abundance and properties of the first galaxies. Thus, the interplay between halo growth and stellar feedback determined which structures survived and which were dismantled by their own stars. By the time the universe was 1 billion years old, the first wave of star formation had left an indelible imprint on its chemistry and thermodynamics. Gas clouds now contained metals and dust, enabling new cooling channels. Stars formed with masses spanning a wide range, including many low-mass stars that would survive for billions of years. These long-lived stars serve as living fossils, preserving information about the conditions in which they formed and providing clues about the early universe. The reionization era likely ended when the combined ultraviolet output of galaxies was sufficient to ionize nearly all hydrogen atoms. After this point, the fraction of neutral hydrogen in the intergalactic medium dropped dramatically. The universe became transparent at all wavelengths, allowing light from distant sources to traverse space largely unimpeded. This transparency is what allows us to observe galaxies and quasars across billions of light-years today. Throughout this narrative, it is important to remember that our knowledge is built from indirect evidence. We cannot directly observe population 3 stars. They lived and died long ago and were too faint and distant for current telescopes. Instead, we infer their existence from the abundance of heavy elements and the properties of old stars in our galaxy. We simulate their behavior in supercomputers and compare the results to observations. This combination of theory and observation allows us to reconstruct the earliest chapters of cosmic history. The story of cosmic dawn is one of transformation. It is the tale of a universe that began uniform and dark and became structured and luminous. Through gravity's persistent pull and the fiery passion of stars, matter assembled itself into ever more complex forms. From the ashes of massive stars rose the ingredients for planets and life. The early universe set the stage for everything that followed. As we contemplate the lives and deaths of the first stars, we are reminded of the cyclical nature of cosmic processes. Creation and destruction are entwined. The death of one generation of stars seeds the birth of the next. This continuous cycle fosters diversity and richness in the cosmos. The heavy elements forged in stellar cores are the building blocks of rocky planets, oceans, and living organisms. We owe our existence to the violent demise of stars billions of years ago. The reionization of hydrogen by the first stars and galaxies also carries a poetic resonance. Light pierced the cosmic fog, turning darkness into transparency. Once invisible to one another, galaxies became visible companions, and their light began to traverse the vast cosmic web. The universe woke up to itself, in a sense, aware through light of its own structure. The echoes of those first photons still reverberate in the diffuse glow of the cosmic background, and in the faint signals we strive to detect. Understanding the formation of cosmic structures requires synthesizing many physical processes. Cosmologists study gravity, hydrodynamics, nuclear physics, radiation transfer, and chemistry. They build numerical simulations that follow billions of particles and cells to mimic the growth of the cosmic web. Observers use telescopes across the electromagnetic spectrum to collect light from the most distant objects. The interplay of theory and observation creates a rich tapestry of knowledge that continues to evolve. Future observations promise to push the frontier of the cosmic dawn even further. The James Webb Space Telescope will peer deeper into space and time, detecting galaxies only a few 100 million years after the Big Bang. Radio arrays will map the distribution of neutral hydrogen during reionization. Upcoming observatories like the Giant Magellan Telescope and the Extremely Large Telescope will resolve individual stars in distant galaxies. These instruments will help answer questions that remain open today. One of the enduring mysteries concerns the nature of dark matter and its role in structure formation. Dark matter does not interact with light, but its gravitational influence is paramount. Its density fluctuations seeded the cosmic web, and its halos provided the gravitational wells in which galaxies formed. Understanding the properties of dark matter, whether it is cold, warm, or something else entirely, remains a key goal. Early structure formation can provide constraints on dark matter models. Another open question relates to the initial mass function of population 3 stars. Were all of them extremely massive, or was there a broader distribution of masses? Did some smaller population 3 stars survive to the present day, hidden among the faintest stars in the Milky Way's halo? Finding such survivors would provide a direct link to the cosmic dawn and help refine models of early star formation. Surveys of metal-poor stars continue to search for these ancient relics. The timing and duration of reionization also hold clues about the efficiency of early galaxies in producing ionizing photons. Were a few bright galaxies responsible for most of the ionization, or was the process driven by many small galaxies? The escape fraction of ultraviolet photons from galaxies depends on complex factors like gas geometry and dust content. Measuring these properties in distant galaxies is challenging but essential for a full understanding of reionization. Cosmic reionization affected not only hydrogen, but also helium. Helium atoms require more energetic photons to ionize, so helium ionization likely occurred later, driven by quasars and active galaxies. Observations of the intergalactic medium at lower redshifts can detect the signatures of helium ionization. This later phase further heats the intergalactic gas and influences the thermal history of the universe. Together, hydrogen and helium ionization shape the environment in which galaxies evolve. The interplay between galaxies and their environment continues beyond the reionization era. Even after the universe became transparent, galaxies continued to influence the intergalactic medium through winds, radiation, and chemical enrichment. Metals and dust expelled by galaxies can travel long distances, spreading the products of stellar nucleosynthesis far from their origins. The intergalactic medium, once pristine, becomes enriched over time, altering cooling rates and the formation of new galaxies. Feedback mechanisms ensure that galaxy growth is self-regulating. When star formation becomes too vigorous, the resulting winds and radiation expel gas, slowing further growth. When gas accumulates, star formation can resume. This balance yields the observed relationship between galaxy mass and star formation rate. Feedback from supermassive black holes operates on larger scales, sometimes shutting down star formation entirely in massive galaxies. The complexity of these feedback loops challenges theoreticians and invites deeper inquiry. The cosmic dawn also invites philosophical reflection. Out of a nearly featureless beginning emerged a universe rich in structure and diversity. Tiny quantum fluctuations, stretched by cosmic inflation, grew into galaxies and clusters. The laws of physics, constant across space and time, governed this transformation with exquisite precision. Within this grand unfolding, the seeds of life were planted by the stars' forges. As we imagine the first stars igniting in the darkness, we sense the poignancy of those brief lives. They lived quickly, burning through their fuel to light up the cosmos. They never knew the worlds that would come from their ashes. Yet without them, planets and people would never exist. In their short lifetimes, they made possible the long, slow unfolding of cosmic history that followed. Their echoes resonate through time in the heavy elements we find in our bodies. The cycle of enrichment continued as subsequent generations of stars formed and died. Each new generation contained more metals, allowing the formation of smaller, longer-lived stars. Planets began to form around these stars, and stable planetary systems emerged. In some small corner of the universe, life eventually arose. The connection between the first stars and the emergence of life underscores the unity of cosmic history. Looking ahead, one can anticipate new discoveries that will refine this narrative. Perhaps we will detect the first direct evidence of population 3 stars through gravitational waves or other messengers. Maybe we will find surviving members of the first stellar generation. Advances in computer simulations will continue to improve our understanding of early star formation and galaxy assembly. Each new insight will add depth to the story of the universe's first light. In the meantime, the cosmic dawn remains a source of wonder and inspiration. It reminds us that even in the darkest times, new light can emerge, transforming the world. It invites us to contemplate the vastness of time and the interconnectedness of all things. By studying the first stars and galaxies, we learn not only about the distant past, but also about ourselves and our place in the cosmos. The journey of discovery continues, guided by curiosity and illuminated by the faint echoes of the universe's earliest moments. Even after reionization, The processes of star formation and chemical enrichment continued to evolve. Stars with different masses followed different pathways, with intermediate mass stars entering the asymptotic giant branch phase. In this stage, helium and hydrogen shell burning cause the star to swell and pulsate. Strong stellar winds carry carbon-rich material into space, creating dust shells around the star. These winds contribute significant amounts of carbon and nitrogen to the interstellar medium, enriching the gas from which new stars will form. When intermediate mass stars shed their outer layers, the exposed cores become white dwarfs composed of carbon and oxygen. Over time, some white dwarfs in binary systems can accrete material from a companion star. If a white dwarf approaches a critical mass known as the Chandrasekhar limit, it can ignite carbon fusion explosively. The resulting Type Ia supernova completely disrupts the white dwarf and produces large quantities of iron group elements. Because these explosions have consistent luminosities, astronomers use them as standard candles to measure cosmic distances. Massive stars experience more complex internal evolution before they explode. After helium is exhausted, the core contracts and heats further, allowing carbon fusion. This is followed by oxygen, neon, and silicon fusion in successive layers, each lasting progressively shorter times. Silicon burning produces an iron core in the final days of the star's life. When the core collapses, neutrinos released in enormous numbers help drive the supernova explosion. The collapsing core rebounds and sends shockwaves that propagate outward, dispersing the star's outer layers. The formation of neutron stars and black holes depends on the mass of the collapsing core. In a neutron star, gravity compresses atomic nuclei so tightly that electrons and protons merge into neutrons. These stars are only about 20 kilometers across, but contain a mass greater than that of the Sun. If the core exceeds a threshold mass, gravity continues its inexorable pull, and nothing can stop the collapse. A black hole forms, creating a region of spacetime from which not even light can escape. Both neutron stars and black holes can be sources of intense radiation and gravitational waves when they interact with companions. Gravitational waves, ripples in spacetime predicted by Einstein's theory of relativity, are created by accelerating masses. The merger of two black holes or two neutron stars produces strong gravitational waves that propagate outward at the speed of light. Detectors like LIGO and Virgo have captured these signals, opening a new window onto the universe. In the future, gravitational wave observatories may detect signals from the collapse of massive population 3 stars or from primordial black holes, providing insights into the earliest epochs. Another messenger from the early universe is the cosmic neutrino background. Neutrinos are nearly massless particles that interact very weakly with matter. They decoupled from the rest of the cosmic plasma within the first second after the Big Bang and have been streaming freely ever since. Although we have not yet detected this background directly, its presence influences the formation of structure and leaves subtle imprints on the cosmic microwave background. Studying neutrinos helps refine models of the early universe and particle physics. In addition to light and neutrinos, cosmic rays travel through the galaxy and beyond. These high-energy charged particles originate from supernova explosions, active galactic nuclei, and possibly exotic processes like the decay of dark matter. When they collide with interstellar gas, they produce showers of secondary particles and contribute to the heating and ionization of the interstellar medium. The study of cosmic rays connects astrophysics with particle physics and continues to reveal new phenomena. As cosmic structures continue to evolve, the interplay between dark matter and baryonic matter remains central. On large scales, the distribution of galaxies traces the underlying dark matter. On smaller scales, baryonic processes like gas cooling, star formation, and feedback can alter the structure of dark matter halos. In particular, repeated outflows driven by supernovae can redistribute dark matter, creating cores rather than cusps in the density profiles of dwarf galaxies. Such interactions illustrate the complex coupling between visible and invisible matter. Numerical simulations are indispensable tools for exploring the formation of structure. Cosmologists run simulations that follow billions of particles and fluid elements over cosmic time, incorporating gravity, hydrodynamics, and radiative processes. By comparing the results with observations, they test models of dark matter and baryonic physics. High-resolution simulations can resolve the formation of individual stars and stellar clusters within galaxies, while large-volume simulations map out the cosmic web on scales of hundreds of millions of light-years. Observationally, deep surveys of the sky reveal galaxies across cosmic history. Space-based telescopes like Hubble and Webb can observe faint galaxies at high redshift, capturing light that left those galaxies billions of years ago. Ground-based telescopes equipped with adaptive optics and spectrographs provide complementary information, such as the velocities of stars and gas, chemical abundances, and the presence of active nuclei. Together, observations and simulations paint a detailed picture of how galaxies grew from tiny seeds into vast systems. The chemical evolution of galaxies is traced by studying the abundance of elements in stars and gas. Spectroscopy allows astronomers to measure the amounts of elements like oxygen, iron, and carbon in different stellar populations. Older stars tend to have lower metallicities, reflecting the composition of the gas from which they formed. Younger stars incorporate more metals, indicating ongoing enrichment. By examining metallicities across galaxies and comparing them with models, scientists infer the history of star formation and feedback. As galaxies grew, they developed internal structures such as bulges, disks, and halos. Bulges, central collections of older stars, form through mergers or the coalescence of giant star clusters. Disks are sites of ongoing star formation and rotation. They often host spiral arms shaped by density waves. Halos consist of old, metal-poor stars and dark matter, extending far beyond the visible disk. The distribution of stars in these components tells a story of a galaxy's past interactions and internal dynamics. The environment in which a galaxy resides influences its evolution. Isolated galaxies can accrete gas from the intergalactic medium and form stars for long periods. Galaxies in groups and clusters experience interactions with neighbors and the cluster's hot gas. Processes such as ram pressure stripping can remove gas from the disks of galaxies, moving through the intracluster medium. Tidal interactions can trigger starbursts or fuel central black holes. Environmental effects thus contribute to the diversity of galaxy properties. The growth of large-scale structures also depends on cosmological parameters, such as the density of matter and the properties of dark energy. Dark energy is a mysterious component of the universe that drives cosmic acceleration. Its influence becomes significant on scales larger than clusters of galaxies. Precise measurements of the cosmic microwave background, galaxy clustering, and supernova distances constrain the amount of dark energy and its equation of state. Understanding dark energy remains a major goal of cosmology, and the early structure formation provides a context for interpreting its effects. The cosmic microwave background itself carries a wealth of information about the early universe. Tiny temperature fluctuations in this background reflect density variations that later grew into galaxies and clusters. Detailed observations of the microwave background's anisotropies, polarization, and spectral distortions provide constraints on the number of light particles, the amplitude of primordial gravitational waves, and the physics of inflation. By connecting the cosmic dawn to the cosmic background, we see a continuous narrative from the earliest moments to the emergence of structure. Gravitational lensing is another powerful probe of cosmic structure. Massive objects like clusters and galaxies bend light from background sources, distorting and magnifying their images. By analyzing these distortions, astronomers can map the distribution of mass, including dark matter. Strong lensing can produce multiple images of a single source, while weak lensing causes subtle shape distortions in many background galaxies. Lensing observations complement other methods and provide direct measurements of the cosmic web's mass distribution. On the smallest scales, the physics of star formation remains a frontier. Within molecular clouds, turbulence, magnetic fields, and radiation interact in complex ways. Dense cores collapse to form stars, while nearby massive stars can trigger or inhibit further collapse. Stellar feedback shapes the internal structure of clouds, carving out cavities and driving turbulent motions. Observations of nearby star-forming regions, combined with simulations, inform models of how stars form in different environments and at different epochs. Planet formation is intimately linked to star formation. Disks of gas and dust around young stars provide the material from which planets arise. Over millions of years, dust particles collide and stick together, forming pebble-sized aggregates. These pebbles drift inward and coalesce into planetesimals, which in turn merge to form planetary cores. Gas giants accrete thick atmospheres from the surrounding disk, while terrestrial planets remain rocky. The chemical composition of the disk, shaped by previous generations of stars, affects the types of planets that can form. The first planets likely formed after the universe had aged enough for second-generation stars to create the required heavy elements. These planets may have been very different from those we know, orbiting low-mass stars in environments rich in radiation and stellar winds. It is possible that some survived to the present day in ancient star clusters. Studying exoplanets across the galaxy reveals a diversity of worlds, hinting at the range of planetary systems that might have existed early on. Planet formation and evolution are thus integral to the cosmic story. Life, as far as we know, emerged on at least one planet around a medium-sized star in a spiral galaxy. The conditions that allowed life to thrive on Earth depend on the chemical and dynamical history of our galaxy. Our Sun formed from gas enriched by countless supernovae and enriched by the ashes of previous stars. It lies in the relatively calm outskirts of the Milky Way, away from the crowded regions where supernovae and black holes could threaten developing life. The cosmic narrative thus connects the first light to the emergence of consciousness. As we trace the history of the universe, we find that small changes early on can have profound consequences later. The amplitude of the initial density fluctuations influences the abundance of galaxies. The metallicity of early stars affects the formation of planets. The timing of reionization impacts the survival of dwarf galaxies. Each parameter is part of a delicate balance that shaped the universe's evolution, reminding us of the intricate web of cause and effect spanning billions of years. Observational cosmology has progressed rapidly in recent decades. Instruments like the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Vera C. Rubin Observatory have catalogued millions of galaxies, mapping the cosmic web with unprecedented detail. Spectroscopic surveys measure galaxy redshifts, enabling three-dimensional maps of the universe. These maps reveal structures such as baryon acoustic oscillations, relics of sound waves in the early universe, that serve as standard rulers for measuring cosmic distances. In parallel, theoretical advances have refined models of galaxy formation and evolution. Semi-analytic models and hydrodynamic simulations incorporate complex processes such as cooling, star formation, feedback, and black hole growth. By adjusting parameters, theorists can reproduce observed galaxy populations and predict new phenomena. Close collaboration between observers and theorists leads to better understanding and more accurate descriptions of the cosmos. The interplay between physics on vastly different scales is a hallmark of cosmology. Quantum fluctuations in the early universe influence the distribution of galaxies millions of light years across. Nuclear reactions in stars produce elements that eventually form planets and living beings. The expansion of space itself affects the formation of structures and the propagation of light. Recognizing and studying these connections deepens our appreciation of the unity underlying cosmic phenomena. As our knowledge expands, so does our sense of mystery. New observations often raise unexpected questions. For example, the detection of galaxies at very high redshift challenges models of how quickly the first stars and galaxies formed. The observed abundance of massive black holes at early times suggests rapid growth mechanisms that are not fully understood. Each discovery adds a piece to the puzzle, but also exposes the edges of our understanding. The history of the universe is not just an academic pursuit. It influences our perspective on existence. The enormity of cosmic time and space dwarfs human scales. Yet our minds are capable of grasping these vast spans and reconstructing events that occurred billions of years ago. The knowledge that the atoms in our bodies were forged in ancient stars can evoke feelings of connection and wonder. Science becomes a bridge between the incomprehensibly large and the intimately personal. Continuing to explore the cosmic dawn will require technological advancements, building larger telescopes, launching space observatories, and deploying networks of gravitational wave and neutrino detectors demand international collaboration. These efforts push the boundaries of engineering and inspire new generations of scientists. They also produce spin-off technologies that benefit society in unexpected ways, highlighting the broader value of fundamental research. Education and outreach play a crucial role in sharing the story of the cosmic dawn. Engaging narratives about the first stars and galaxies can inspire young minds to pursue studies in science and engineering. Visualizations of simulations and observations help convey complex concepts in accessible ways. Public appreciation of cosmology fosters support for scientific endeavors and cultivates a culture that values curiosity and knowledge. Cultural perspectives on the universe's origins vary across societies and times. Myths and stories often speak of a primordial darkness, followed by the emergence of light. Modern cosmology resonates with these themes, albeit grounded in empirical evidence and theoretical models. The intertwining of science and culture enriches both, offering new metaphors and deeper understanding. The cosmic dawn thus belongs to humanity's collective heritage, transcending boundaries and inspiring awe. Looking back also encourages us to look forward. The physical processes that illuminated the early universe continue today in distant corners of space. New stars are forming, galaxies are interacting, and black holes are growing. The cycle of creation and destruction is ongoing, and our observations capture only a snapshot in this dynamic story. Recognizing the transience and continuity of cosmic events prompts humility and curiosity. In the context of cosmic time, even the formation of galaxies is a fleeting moment. Over trillions of years, stars will exhaust their nuclear fuel, galaxies will grow dim, and the universe will evolve into new phases. Dark energy may continue to accelerate the expansion, isolating galaxies from one another. In contrast, primordial black holes, if they exist, could persist for much longer. Contemplating these distant futures can be both unsettling and profoundly fascinating. Returning to the first stars, one wonders about their appearance and the skies under which they shone. They would have radiated intensely in ultraviolet light, illuminating their immediate surroundings with a bluish-white glow. The absence of metals would have made their atmospheres relatively transparent, affecting their spectra. Observers on a nearby protoplanet, had any existed, would have seen a sky filled with a few enormous, brilliant stars and vast regions of darkness. Imagining these scenes connects us emotionally to an epoch far removed from our own. The interplay between cosmic scales and human scales is particularly striking when we consider time. 1,000,000 years, the approximate lifespan of a massive population 3 star, is a long time compared to human lifetimes. Yet it is a heartbeat in cosmic terms. Billions of years of cosmic evolution pass, while our species emerges, struggles, and contemplates its origins. This juxtaposition invites reflection on our place in the grand scheme of things. Understanding early star formation also informs our search for life beyond Earth. Planets that formed early in the universe's history may have been bathed in intense radiation and subjected to frequent supernovae. Such environments might have been hostile to life as we know it. Conversely, planets forming in calmer regions around long-lived stars could have more stable conditions. By studying the distribution and properties of exoplanets, we gain insight into the potential for life across cosmic time. Astrobiology intersects with cosmology when considering the habitability of the universe. The era of peak star formation, when galaxies were most active, occurred several billion years after reionization. Since then, star formation has declined, but the abundance of long-lived stars increases the number of potential habitable zones. The chemical enrichment of the interstellar medium ensures that terrestrial planets can form. Thus, the cosmic timeline influences the likelihood and distribution of life. Exploring the cosmic dawn also has implications for fundamental physics. The properties of dark matter and dark energy, the nature of inflation, and the behavior of neutrinos all influence structure formation. Precise measurements of early galaxies, reionization, and the cosmic microwave background can constrain these parameters. In this way, astrophysics serves as a laboratory for testing theories of particle physics and gravity under conditions inaccessible on Earth. One intriguing possibility is that dark matter might interact weakly with normal matter or even self-annihilate, producing gamma rays or other signatures. If such processes were significant during the cosmic dawn, they could have affected the thermal and ionization state of the intergalactic medium. Observational constraints on reionization can therefore limit models of dark matter. Similarly, the existence of primordial black holes as a dark matter candidate would influence early structure formation and could leave detectable imprints. The first light also contains information about primordial magnetic fields. If magnetic fields existed in the early universe, they could influence the collapse of gas and the transport of angular momentum. Observations of galaxies and clusters today show pervasive magnetic fields. The origin of these fields is still debated, with possibilities ranging from amplification of tiny seed fields produced during inflation to generation by dynamos in galaxies. Understanding magnetic field evolution requires connecting the cosmic dawn to later epochs. Cosmologists also examine the possibility of non-standard cosmological models, alternatives to cold dark matter, such as warm dark matter or fuzzy dark matter, predict different behavior on small scales. The abundance and properties of dwarf galaxies and the timing of reionization can discriminate between these models. Similarly, modifications to gravity at large scales might affect the growth of structure. Studying the early universe provides a testing ground for such theories. The synergy between different observational probes is essential for building a coherent picture. For example, combining quasar spectra with measurements of the cosmic microwave background and galaxy clustering can refine constraints on reionization. Cross-correlating 21-centimeter maps with galaxy surveys can reveal how ionized regions correlate with galaxies. Coordinated analyses harness the power of multiple datasets and reduce uncertainties. Technological innovations also enable new kinds of observations. For instance, spectroscopy on extremely faint sources requires sensitive detectors and adaptive optics to correct for atmospheric distortions. Machine learning algorithms help identify distant galaxies in large datasets. High-performance computing allows simulations with unprecedented resolution. As technology advances, so too does our ability to explore the cosmic dawn. As we compile observations across the electromagnetic spectrum, we must also interpret them with care. Light from distant objects is stretched by cosmic expansion, and intervening gas can absorb or scatter certain wavelengths. Dust within galaxies can redden and dim light, complicating measurements. Correcting for these effects requires detailed modeling and can introduce uncertainties. The challenge of extracting accurate information encourages the development of refined techniques. The narrative of cosmic evolution is not linear. It is a tapestry woven from many threads. Processes at different scales and times intertwine. The formation of a galaxy depends on the properties of its local environment and its merger history. The growth of a black hole influences the gas dynamics on galactic scales. The emergence of planetary systems depends on both local conditions and the broader history of star formation. Recognizing these interconnections enriches our understanding. As a thought experiment, imagine rewinding cosmic time and letting it play out again. Would the same structures form? The laws of physics remain the same, but the chaotic nature of gravity and fluid dynamics implies that details might differ. Some galaxies might form earlier or later. Certain clusters might not exist at all. Yet the overall pattern of a cosmic web, stars, galaxies, and clusters would still emerge. This interplay of determinism and randomness is part of the universe's beauty. Star formation rarely occurs in isolation. In the early universe, clouds of gas collapsed into dense clusters where multiple stars ignited nearly simultaneously. These clusters were the nurseries of luminous giants and smaller companions, bound together by gravity and illuminated by their collective radiation. Some clusters dispersed when their most massive members exploded. Others survived for billions of years as globular clusters orbiting modern galaxies. The heavy elements forged in the hearts of the first stars were scattered by their violent deaths. Each supernova seeded the surrounding gas with carbon, oxygen, and iron, enriching the material from which later generations of stars would form. Over cosmic time, this chemical enrichment built up the periodic table in stellar furnaces. The distribution of metals became a record of past generations, telling a story of continual recycling. When gas cooled within the gravitational wells of dark matter halos, it condensed into rotating disks and irregular clouds. Turbulence and shock waves triggered the collapse of denser pockets, leading to the birth of stars within nebula. In small halos, a single supernova could blow out much of the gas, halting star formation. In larger halos, gravity held on to the gas, allowing galaxies to build populations of stars over hundreds of millions of years. Early galaxies were clumpy and irregular, their shapes sculpted by streams of infalling gas and frequent mergers. Over time, some settled into rotating disks where spiral arms emerged, while others became elliptical conglomerates, dominated by random motions. Interactions and environment determined whether a galaxy retained its gas or exhausted it in bursts of star formation. The diversity of shapes we see today traces back to these formative processes. Among the remnants of early massive stars were black holes, tiny seeds destined to grow into giants. As gas funneled toward galactic centers, these seeds accreted matter and radiated energy, becoming active galactic nuclei that outshone their host galaxies. The outflows from accretion disks shaped the surrounding gas, sometimes quenching star formation, sometimes triggering new bursts. The dance between a galaxy and its central black hole became one of coevolution. The feedback between star formation and the interstellar medium played a decisive role in the early universe. When the first stars exploded, shock waves heated and expelled gas from small halos. In larger systems, supernova-driven winds stirred the gas but did not unbind it, injecting turbulence that could both suppress and catalyze further star formation. This feedback regulation prevented the immediate collapse of all gas, stretching the era of star formation over billions of years. On larger scales, matter did not distribute uniformly, but assembled into a web of filaments and nodes. Gravity drew dark matter together, and gas followed along, flowing into the intersections where galaxies formed. The filaments served as highways for cold streams of gas, replenishing galaxies with fresh material. The cosmic web thus provided the scaffolding for galaxies and clusters, linking individual systems into a vast network. The reionization of the intergalactic medium left behind relics that astronomers hope to detect. Neutral hydrogen atoms emit radio waves at a wavelength of 21 centimeters, and before reionization, this signal filled space. As the first stars and galaxies ionized the gas, bubbles devoid of this emission grew and merged. By mapping the 21 centimeter signal across the sky, future surveys aim to trace the progression of reionization and reveal the structure of the cosmic dawn. To observe these faint signals, astronomers build arrays of radio antennas spread over vast distances and design instruments capable of detecting extremely small fluctuations. Space telescopes shielded from Earth's atmosphere capture infrared light from primordial galaxies, while ground-based spectrographs analyze quasar spectra to probe intergalactic gas. Each tool offers a different window on the early universe. Together, they form a complementary suite of instruments for cosmic archaeology. The patterns that emerge in the distribution of matter are reminiscent of structures on smaller scales. In a star-forming region, filaments of gas feed nascent stars. On cosmological scales, filaments of the cosmic web feed galaxies. This self-similarity hints at underlying physical processes that operate across many orders of magnitude. Recognizing these analogies enriches our appreciation of nature's coherence. Beyond light, Other messengers carry information about the early universe. A sea of primordial neutrinos permeates space, relics from the first seconds after the Big Bang. Ripples in spacetime known as gravitational waves travel unimpeded across the cosmos, bringing news of merging black holes and potentially of processes at cosmic dawn. As detectors become more sensitive, they may open new avenues for exploring the unseen universe. The phenomena observed in astrophysics are intimately connected to the properties of fundamental particles. The abundance of dark matter halos reflects the nature of the dark matter particle, while the cooling of gas depends on atomic physics. Neutrinos streaming from supernovae carry away energy and influence the outcome of the explosion. By studying astrophysical objects, we gain indirect insight into particle physics and vice versa. Magnetic fields thread through galaxies and clusters, shaping the motion of charged particles and the propagation of cosmic rays. These fields may have originated from tiny seeds amplified over billions of years, or from processes in the early universe. Cosmic rays themselves, accelerated in supernova remnants, are part of the energy budget of the interstellar medium. Understanding magnetism and cosmic rays adds another layer to the story of structure formation. The accumulation of heavy elements over time not only enriches stars, but also affects the cooling of gas. Metals emit radiation efficiently, allowing gas clouds to collapse more readily and form lower mass stars. This shift in cooling properties marks the transition from the primordial era to a more chemically diverse universe. As metallicity increased, the likelihood of forming planets with rocky surfaces also grew. A key property of star-forming regions is the distribution of stellar masses, known as the initial mass function. In the pristine conditions of the early universe, the absence of metals meant that cooling was less efficient, favoring the formation of very massive stars. Later, as metals accumulated, the mass function shifted toward lower masses, producing a diversity of stars like those in the Milky Way. This change had profound consequences for chemical evolution and feedback. Galaxies do not live in isolation. Their properties are influenced by their surroundings. In dense clusters, interactions and the pressure of hot intracluster gas can strip galaxies of their star-forming material, quenching their ability to make new stars. In contrast, galaxies in less crowded environments retain their gas for longer and can continue to form stars at a leisurely pace. The cosmic environment thus shapes the life history of galaxies. When galaxies interact or merge, tidal forces distort their shapes and funnel gas toward the center. The compression of gas triggers intense bursts of star formation, lighting up the galaxy in a transient blaze. Eventually, the merged system settles into a new equilibrium, perhaps as an elliptical galaxy. These interactions are frequent in the early universe, contributing to the rapid buildup of stellar mass. Galaxies grow not only by merging, but also by accreting gas from their surroundings. Filaments of the cosmic web feed cold streams directly into galactic disks. This continuous supply allows sustained star formation over billions of years. Without accretion, galaxies would quickly exhaust their gas and fade. The interplay of feedback and environment determines how efficiently galaxies convert gas into stars. In small halos, feedback can drive winds that escape into the intergalactic medium. In massive clusters, gravitational potential wells trap outflows, enriching the hot intracluster medium. Feedback also spreads metals into the surroundings, affecting the next generation of structure formation. The global rate of star formation in the universe has changed over time. After the initial rise following the cosmic dawn, star formation increased as galaxies grew larger and more numerous, peaking several billion years later before gradually declining. This decline reflects the depletion of cold gas and the influence of cosmic expansion. The history of star formation is a key thread in the tapestry of cosmic evolution. Heavy elements forged in ancient stars are the building blocks of planets and life. When supernovae and stellar winds enriched the interstellar medium, they provided the iron for Earth's core and the carbon for our bodies. Each rocky planet is a testament to the chemical heritage of prior generations of stars. Without the contributions of the cosmic dawn, the ingredients for life would be scarce. We who ponder these distant epochs do so from within the universe, using matter forged in long-dead stars. Our ability to reconstruct the cosmic dawn is akin to archaeology on a vast scale, piecing together clues left in light and matter. Observing distant galaxies is like looking back in time, as their light has traveled billions of years. In this way, the universe serves as its own historian. The cycles of birth and death that govern stars and galaxies mirror broader patterns of renewal. A star condenses from a cloud, radiates for millions or billions of years, then returns material to space via winds or explosions. Galaxies coalesce, form stars, exhaust their gas, and merge to form larger structures. Each cycle leaves imprints on the surrounding cosmos, shaping the landscape for what comes next. While the laws of physics are deterministic, the outcomes of cosmic evolution include elements of chance. Tiny quantum fluctuations during inflation seeded the density variations that grew into galaxies. The timing of a merger, or the presence of a nearby quasar, can alter a galaxy's fate. Recognizing the interplay of necessity and contingency adds depth to our understanding of cosmic history. The story of the universe is both scientific and poetic. We use equations and simulations to model processes, yet we also speak of stars, forging elements, and galaxies, weaving a cosmic web. These metaphors help bridge the gap between abstraction and intuition. The narrative we craft reflects our desire to find meaning in the vastness. As we prepare to continue the journey, it is important to remember that the cosmic dawn set the stage for everything that followed. The first stars, the enrichment of gas, the assembly of galaxies, and the reionization of the universe were necessary preludes to later structure formation. In the next part, we will follow these structures as they evolve and interact across billions of years. The path forward is illuminated by the echoes of the first light. Our story, thus far, has followed the rise of structure from the Dark Ages through reionization and the growth of galaxies. Beyond this stage lies the continuing evolution of galaxies, the formation of galaxy clusters, and the eventual dominance of dark energy. Each era offers its own mysteries and discoveries. The universe is dynamic and ever-changing, and our understanding of it is likewise evolving. We stand at a moment in cosmic time, able to look back and forward, connecting dots across billions of years. In the next part of our journey, we will delve deeper into the structures that formed after reionization, exploring how galaxies assembled into the vast tapestry we observe today. We will examine how galaxies transformed over time, how clusters and superclusters emerged, and how the expansion of the universe continues to shape the cosmos. The story of the expanding universe is far from over. The light from the first stars still echoes through the ages, guiding us forward into the next chapter. As our journey through cosmic history continues, the narrative gently drifts from the primordial fireball into the modern era of discovery. The previous chapter left us contemplating a cooling universe filled with nascent atoms and photons journeying freely. Now, in the quiet light of those scattered rays, we turn our gaze outward. The night sky, once thought to be static and eternal, hides motions subtle and profound. Human curiosity and ingenuity would soon reveal that galaxies are not fixed beads in a cosmic tapestry, but are instead sliding away from one another like ripples on a pond. The gentle whisper of expanding space would change our understanding forever. In the early decades of the 20th century, astronomers peered through telescopes perched high on remote mountaintops. Among them stood Edwin Hubble, a careful observer who measured faint pulsations in the light of distant nebulae. He relied on the work of Henrietta Leavitt, who had discovered that certain variable stars follow a consistent relationship between how bright they appear and how long they take to brighten and dim. By measuring the period of such a star, an astronomer could infer its intrinsic brightness and thus its distance. Hubble applied this method to luminous stars in spiral nebulae and found that those fuzzy patches of light were far beyond the bounds of our own Milky Way, each one a distant island of stars. These newfound galaxies also displayed peculiar colours. Vesto Slipher, working at Lowell Observatory, had measured that some nebulae emitted light that was reddened compared with nearby stellar light. This redshift, as it came to be known, was interpreted as an effect of motion. The wavelengths of light stretch as the source moves away. Hubble combined the distances he measured with the redshifts recorded by Slipher. When he plotted distance against the amount of reddening, he noticed a remarkable trend. The farther away a galaxy seemed to be, the faster it appeared to recede. This simple plot held profound implications. Instead of a universe where galaxies drift randomly, the data implied a systematic expansion. In 1929, Hubble published his findings, revealing that more distant galaxies recede more rapidly from us. This relationship, now called the Hubble law, provided the first observational basis for the idea that space itself is expanding. The conclusion was startling. The fabric of the universe is not static, but stretching, carrying galaxies with it like raisins embedded in rising dough. Such a vision would soon become central to cosmology. The Hubble law is often expressed as a linear relationship. The recession velocity of a galaxy increases in proportion to its distance. Though early measurements were crude and the constant of proportionality was uncertain, the trend was unmistakable. It suggested a dynamic universe whose scale is changing with time. Coupled with general relativity, this relation naturally led to the concept of a universe that emerged from a compact state and has been expanding ever since. The picture of an expanding cosmos elegantly explained other observations and provided a framework for linking cosmic history with physical processes. As astronomers refined distance measurements and collected spectra from more galaxies, the scatter in the data reduced and confidence in cosmic expansion grew. Observatories around the world measured redshifts from galaxies in various directions, and the trend remained consistent. The expansion did not favor any particular direction, indicating that no special place or center existed. Everyone sees other galaxies receding, and each observer would measure the same pattern. This uniformity became one of the cornerstones of cosmology. By the mid-20th century, the idea of a dynamic universe had replaced the previously favored static models. Theoretical physicists like George Gamow and Georges Lemaitre had suggested that a universe that expanded must have been denser and hotter in the past. A primeval explosion, or Big Bang, would account for such a beginning. If true, remnants of that hot phase might still be detectable. At this point, the narrative flows naturally towards a new form of evidence, a faint glow that fills the sky. Our eyes perceive only a narrow band of the electromagnetic spectrum, but the universe hums with radiation across a vast range of wavelengths. Radio engineers Arno Penzias and Robert Wilson discovered something unexpected in 1965 while calibrating an antenna at Bell Laboratories. They detected a persistent hiss coming from all directions, stronger than any known sources could explain. After ruling out interference from equipment and even pigeon droppings, they realized they had found the cosmic microwave background. It was the afterglow of the Big Bang, cooled by eons of expansion. For years, this relic radiation appeared nearly uniform. Its temperature measured around 2.7 Kelvin, only a few degrees above absolute zero. If the universe had been hotter and denser in its youth, its expansion would have stretched the wavelengths of the primordial light to microwave frequencies by the present day. Observations confirmed that the spectrum of this background follows that of a perfect blackbody, offering strong support for the hot Big Bang model. But such uniformity hides subtle patterns. Astronomers theorize that tiny fluctuations in density in the early universe would have left imprints on the microwave background. Where matter was slightly denser, gravity would have slowed the expansion and left a cooler spot. Where matter was slightly rarer, the expansion would have been slightly faster, leaving a hotter spot. These small temperature variations are the seeds from which galaxies later grew. Detecting them would test theories of cosmic structure formation. In 1989, NASA launched the Cosmic Background Explorer satellite, designed to map the microwave background in detail. After 4 years of observations, COBE detected variations in temperature at the level of 1 part in 100,000. The mottled pattern displayed a mix of hot and cold regions across the sky. These anisotropies revealed that the early universe contained slightly overdense regions and slightly underdense regions. With time, gravity would cause matter to fall toward the dense regions, eventually forming galaxies and clusters. The success of COBE inspired a series of more sensitive measurements. Balloon-borne experiments like Boomerang and ground-based instruments like the MATI/TOCO experiment measured the anisotropies with higher resolution. Their data indicated that the largest fluctuations occurred at angular scales of about 1 degree on the sky. This scale corresponds to the largest sound waves that could have traveled in the dense plasma before it cooled. Combined with other cosmological data, these measurements implied that the geometry of space is nearly flat. If the universe were curved, these acoustic peaks in the microwave background would appear at different angular scales. A closed universe would make them appear larger, while an open universe would make them appear smaller. The observations favored neither extreme, supporting a flat universe where space is not curved on large scales. This result matched theoretical expectations from inflation, an earlier phase of accelerated expansion. The microwave background thus carries fossil information about the geometry and content of the cosmos. In the early 21st century, the Wilkinson Microwave Anisotropy Probe refined our understanding further. With improved detectors and 9 years of data, WMAP measured the anisotropies across the whole sky with exquisite precision. The map revealed a web of temperature differences that matched predictions of the Big Bang and inflation. It also provided an accurate value for the Hubble constant and the age of the universe. Even more detailed observations came from the Planck satellite, launched by the European Space Agency in 2009. Planck carried instruments that could detect polarization in the microwave background, a property that encodes information about the scattering of photons by electrons in the early universe. Polarization patterns also help distinguish between different models of cosmic inflation. Planck's high resolution and sensitivity allowed astronomers to detect temperature fluctuations and polarizations across multiple frequency bands. The cosmic microwave background formed when the universe was only about 380,000 years old, a mere blink after the Big Bang compared with its current age. At that time, the temperature was about 3000 Kelvin, and electrons combined with protons to form neutral hydrogen atoms. With electrons bound into atoms, photons were no longer constantly scattered. The universe became transparent, allowing light to travel freely. Over billions of years of expansion, this light stretched from visible wavelengths to microwaves, cooling to its present temperature. Planck and WMAP confirmed that tiny temperature fluctuations trace the seeds of stars and galaxies. They found that the pattern of polarization follows that of the temperature anisotropies, reflecting the distribution of matter in the early universe. These results not only strengthened the case for the Big Bang, but also provided an inventory of the universe's contents. By comparing the heights and positions of the acoustic peaks in the power spectrum, cosmologists inferred the proportions of ordinary matter, dark matter, and dark energy. One of Planck's most striking results was its measurement of the cosmic energy budget. It revealed that ordinary matter, atoms that make up stars, gas, dust, and planets, accounts for less than 1/20th of the universe's total mass energy content. About a quarter of the universe appears to consist of dark matter, an invisible substance that exerts gravitational pull but does not emit light. The remainder, roughly 2/3, appears to be dark energy, a mysterious component responsible for accelerating cosmic expansion. The microwave background thus serves as a time capsule. Tiny ripples in its temperature distribution record the primordial density variations. These imprints allow scientists to test theories of cosmic inflation, measure the total amount of matter and energy, and deduce whether the universe is flat or curved. The near-flat geometry suggested by CMB anisotropies implies that the total mass-energy density is close to the critical density. But visible matter contributes only a small fraction, raising the question of what else fills space. To complement observations of cosmic expansion and the CMB, astronomers turn to the motions of stars within galaxies. According to Newtonian dynamics and general relativity, the rotation speed of stars in a galaxy should decline with distance from the center once most of the mass is enclosed. Instead, observations show that rotation curves remain flat or even rise toward the outskirts. This discrepancy implies that additional unseen mass surrounds galaxies, forming halos that extend far beyond the visible disk. The evidence for dark matter accumulates across many scales. In galaxy clusters, 3 independent measurements, galaxies' velocities, X-ray emitting gas, and gravitational lensing, indicate far more mass than the luminous matter alone can account for. Gravitational lensing measures the way mass bends light from distant sources. The amount of bending matches the predictions if clusters contain about 5 times more dark matter than ordinary matter. Strong lensing arcs show mass distributions offset from hot gas in mergers like the Bullet cluster, challenging modified gravity models and favoring dark matter. Dwarf galaxies and low-surface brightness galaxies are dominated by dark matter, as their visible matter alone cannot explain observed velocities. Elliptical galaxies exhibit mass profiles that require substantial dark matter halos to account for the motions of their stars. Dwarf spheroidal satellites of the Milky Way show especially large mass to light ratios, indicating that they are embedded in dense dark matter halos. Such systems serve as laboratories for studying dark matter properties on small scales. Galaxy rotation curves and cluster dynamics are not the only hints of dark matter. The pattern of temperature fluctuations in the cosmic microwave background is sensitive to the amount of dark matter because it influences how gravity shapes sound waves in the early universe. Simulations of cosmic structure formation show that without dark matter, primordial fluctuations would not grow quickly enough to form galaxies and clusters by the present day. Dark matter provides gravitational scaffolding, allowing ordinary matter to collapse into structures after recombination. The nature of dark matter remains elusive. Candidate particles include weakly interacting massive particles that interact only through gravity and the weak nuclear force. Direct detection experiments search for rare collisions between such particles and atomic nuclei deep underground. Axions, ultralight particles proposed to solve the strong CP problem in quantum chromodynamics, offer another possibility. Primordial black holes formed in the early universe provide yet another candidate, although their abundance is tightly constrained by microlensing and gravitational wave observations. Alternative theories of gravity have been proposed to explain galactic rotation curves without dark matter. Modified Newtonian dynamics suggests that at very low accelerations, the gravitational force deviates from Newton's law. Tensor vector scalar theories provide a relativistic extension of this idea. Emergent gravity posits that gravity arises from thermodynamic considerations and may behave differently on cosmic scales. Although these theories can fit certain data, they struggle to account for the full range of observations, including galaxy clusters, lensing, and the cosmic microwave background. Most astrophysicists conclude that some form of dark matter is still required. Alongside dark matter, another mysterious component shapes the cosmos: dark energy. In the late 1990s, two teams studying Type Ia supernovae discovered that distant supernovae appeared dimmer than expected in a decelerating universe. These supernovae serve as standard candles, objects of known brightness whose observed dimming reveals their distance. Comparing the distances to their redshifts showed that the expansion of the universe is accelerating, not slowing. This surprising finding implies that a form of energy with negative pressure is driving the cosmic acceleration. Type Ia supernovae are valuable because the explosions have nearly uniform peak luminosities. A carbon-oxygen white dwarf accretes matter from a companion star. When it approaches the Chandrasekhar mass, carbon ignites explosively, unbinding the star. Observations show slight variations in brightness that correlate with the shape of the light curve. Supernovae that fade more slowly are intrinsically brighter. By correcting for this relation, astronomers standardize these events. Distant supernovae thus act as cosmic beacons, illuminating the expansion history. The discovery of cosmic acceleration was independently reported by the High-Zer Supernova Search Team and the Supernova Cosmology Project. Their work involved careful control of systematic errors, from interstellar dust to supernova evolution. The results were cross-checked and scrutinized, and the conclusion withstood the tests. The acceleration implies that the energy density of the vacuum is non-zero, or that the gravitational law differs on large scales. The simplest explanation is a cosmological constant, the same term that Einstein once introduced to achieve a static universe. Combining supernova observations with the cosmic microwave background and large-scale structure surveys solidified the picture of a universe dominated by dark energy and dark matter. The microwave background indicates that the universe is spatially flat, while matter accounts for only about 30% of the critical density. Large-scale structure observations require a smooth component to slow the growth of structure less than would be expected in a matter-only universe. Together, these lines of evidence point to a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The nature of dark energy is one of the deepest puzzles in physics. The cosmological constant can be interpreted as the energy of the vacuum, yet quantum field theory predicts a value many orders of magnitude larger than observed. This mismatch is known as the cosmological constant problem. Alternative ideas include dynamic fields, such as quintessence, that evolve over time, or modifications to gravity that become apparent only on large scales. Determining whether dark energy is constant or varying with time is a major goal of current and future observations. Beyond the canonical models, physicists explore interactions between dark energy and dark matter. In such models, energy exchange between the components could alter the expansion history and the growth of structures. Massive neutrinos play a role as well, suppressing structure on small scales. The interplay between dark energy, dark matter, and neutrinos offers a rich phenomenology that can be tested with cosmic microwave background data, galaxy surveys, and lensing measurements. The combination of multiple data sets allows subtle effects to be teased out. The integrated Sachs-Wolf effect provides a way to detect dark energy through the microwave background. As photons travel through gravitational potentials, their energies shift slightly. In a universe dominated by matter, the potentials remain constant, and the net effect cancels. When dark energy causes the potentials to decay over time, photons gain or lose energy depending on the timing of their passage. By correlating microwave background maps with galaxy surveys, astronomers detect this subtle signal, providing independent evidence for dark energy. The ultimate fate of the universe depends on the properties of dark energy. If dark energy remains constant, the universe will continue to expand, cooling and diluting. This scenario is often called the Big Freeze. If dark energy evolves or has an equation of state less than -1, the expansion could accelerate so rapidly that it tears apart galaxies, stars, and eventually atoms in a big rip. Alternatively, dark energy could decay or change sign, causing the expansion to slow or reverse. The variety of possibilities underscores how much remains unknown. Cosmic acceleration introduces horizons similar to those around black holes. Beyond a certain distance, objects recede faster than light relative to us, meaning their light will never reach us. Over time, more galaxies cross this cosmic event horizon, leaving only the local group bound by gravity. Future astronomers, living trillions of years from now, might see nothing beyond the Milky Way and Andromeda merger remnant. Their view of the cosmos would be limited, highlighting the unique perspective we enjoy today. To better understand dark energy and dark matter, upcoming surveys will map the universe with unprecedented depth and precision. The European Space Agency's Euclid mission will survey billions of galaxies over a third of the sky, measuring weak lensing and baryon acoustic oscillations. NASA's Nancy Grace Roman Space Telescope will conduct wide-field infrared surveys of supernovae and galaxies. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will image the southern sky every few nights, discovering billions of galaxies and transient events. These projects aim to tighten constraints on the properties of dark energy and to map the distribution of dark matter. As we contemplate these surveys, we are reminded of the interplay between human curiosity and the universe's vastness. Each new instrument extends our senses, revealing patterns and anomalies that challenge our understanding. The names we give to unknown components, dark matter and dark energy, are placeholders for deeper truths. They remind us that the cosmos still holds mysteries as profound as those faced by Hubble a century ago. The path toward understanding is long and winding, and each discovery opens new questions. The story of the universe is not just about distant galaxies and exotic particles. It is also about our place within this grand tapestry. The atoms in our bodies were forged in stars whose formation depended on dark matter scaffolding. The accelerated expansion of space shapes the cosmic future in which our descendants may live. When we study the cosmos, we are not merely peering outward, but also inward, exploring the processes that allow life to emerge. The connection between cosmic and human history lends a sense of wonder to the scientific quest. With each measurement, we refine our models and adjust our expectations. We build detectors deep underground, launch satellites to the far side of the moon, and develop theories that blend quantum mechanics with cosmology. The pursuit of knowledge is collaborative and often slow, filled with false starts and revisions. Yet the quiet, persistent effort of scientists around the world steadily illuminates the darkness. In this way, the universe teaches us patience and humility. Edwin Hubble's path to astronomy was not straightforward. He initially studied law and served in the First World War, before turning his attention to the sky. His disciplined approach and physical stature gave him a commanding presence at Mount Wilson Observatory. Hubble meticulously measured Cepheid variables, combining the excitement of exploration with the rigor of careful calibration. His career arc reflects the serendipitous paths by which individuals find their calling, blending personal history with the larger story of cosmic discovery. In the early 20th century, astronomers debated whether spiral nebulae were part of the Milky Way or distant island universes. This great debate between Harlow Shapley and Heber Curtis highlighted uncertainties about cosmic scale. Shapley argued that the Milky Way was enormous and that nebulae were within it, while Curtis contended that the nebulae were separate galaxies. The debate ended inconclusively, but subsequent distance measurements vindicated Curtis and opened the universe to a myriad of galaxies beyond our own. The shift in scale changed our perspective on humanity's place in the cosmos. The redshifts that Hubble plotted were measured by examining spectral lines. Each chemical element produces a pattern of lines at specific wavelengths. When these lines are shifted toward longer wavelengths, it indicates motion away from the observer. Astronomers understood that the shift could be due to Doppler motion or to the expansion of space itself. In an expanding universe, light is stretched along with space, and the redshift tells us how much the universe has expanded since the light was emitted. This subtle difference between motion through space and the stretching of space underpins modern cosmological interpretation. Einstein initially introduced a cosmological constant into his equations of general relativity to achieve a static universe. When Hubble's observations suggested expansion, Einstein reportedly called this term his greatest blunder. Yet the idea of a cosmological constant resurfaced decades later as a possible explanation for the accelerating universe. The Belgian priest and physicist Georges Lemaitre independently derived expanding solutions and connected them with observations before Hubble's publication. Such historical twists remind us that theoretical concepts can lie dormant until observations breathe new life into them. Alexander Friedmann derived the equations governing an expanding universe from Einstein's theory. These equations describe how the scale factor, an ever-changing measure of cosmic size, evolves with time in response to matter, radiation, curvature, and any cosmological constant. Different combinations of these ingredients yield universes that expand forever, recollapse, or approach a steady state. By comparing models with data, cosmologists infer the relative proportions of cosmic components. The notion of a dynamic scale factor helps connect abstract mathematics to the observable sky. Measuring the universe relies on a distance ladder of overlapping techniques. Parallax uses Earth's orbit as a baseline to determine distances to nearby stars. Cepheid variables extend the reach to nearby galaxies. RR Lyrae stars and red giant branch tips offer additional rungs. The Tully-Fisher relation connects the rotation speed of spiral galaxies to their luminosity, while the Faber-Jackson relation does the same for elliptical galaxies. Each rung must be carefully calibrated so that uncertainties do not accumulate, and this ladder underpins the measurement of the Hubble constant. Modern determinations of the Hubble constant reveal a tension between early and late universe measurements. Cosmic microwave background data, combined with a cosmological model, yield a value around 67 kilometers per second per megaparsec. Local measurements using cepheids and supernovae find a higher value near 73 kilometers per second per megaparsec. This discrepancy may point to unrecognized systematic errors or to new physics beyond the standard cosmological model. The tension has spurred intense observational and theoretical work, illustrating how small differences can hint at deep questions. Besides photons, the early universe also contained neutrinos that decoupled when it was just 1 second old. These relic neutrinos form a cosmic background that permeates space, analogous to the microwave background, but even harder to detect. The cosmic neutrino background affects the expansion rate in the early universe and leaves subtle imprints on the microwave anisotropy pattern. Future experiments may detect these neutrinos indirectly or directly, adding another strand of information about the Big Bang. The ghostly particles carry memories from the first moments of cosmic history. Polarization of the cosmic microwave background arises when radiation scatters off electrons in a non-isotropic way. The resulting patterns can be decomposed into E-mode and B-mode components. E-modes have been measured accurately and reflect density fluctuations, while B-modes could reveal gravitational waves from inflation if detected. Experiments like BICEP, POLAR, BEAR, and the Simons Observatory are refining measurements of polarization. Distinguishing primordial B-modes from foreground dust is challenging, but offers a potential window into physics at unimaginably high energies. Large-scale structures between us and the surface of last scattering deflect the paths of microwave photons. This gravitational lensing subtly smooths the anisotropy pattern and introduces non-Gaussian features. By measuring distortions in the CMB, scientists reconstruct maps of the intervening mass distribution. These maps complement galaxy surveys and provide a way to probe dark matter without reliance on luminous tracers. CMB lensing thus turns cosmic microwave photons into messengers that carry information about the invisible landscape they traverse. While the cosmic microwave background is remarkably uniform on large scales, careful analyses have identified potential anomalies. The quadrupole and octupole modes display alignments dubbed the axis of evil, and a cold spot in the southern hemisphere remains puzzling. Some consider these features to be statistical flukes caused by cosmic variance, while others speculate about new physics or foreground effects. Ongoing work seeks to test whether these anomalies persist in other datasets. The possibility of unexpected patterns keeps cosmologists attentive to subtle clues. After recombination, the universe entered a dark age, devoid of luminous sources. Over hundreds of millions of years, the first stars and galaxies formed, emitting ultraviolet radiation that rayonized the intergalactic medium. This epoch of rayonization ended the cosmic dark age and left traces in the microwave background polarization. Observations of distant quasars and galaxies show that rayonization was an extended and patchy process. The timing and duration of this transition provide insights into the properties of early stars and the growth of structure. Neutral hydrogen emits radiation at a wavelength of 21 centimeters due to a flip in the electron's spin. Observing this line across cosmic time offers a promising way to map the distribution of matter from the Dark Age through reionization. Instruments like the Hydrogen Epoch of Reionization Array and experiments like EDGES aim to detect the global 21 centimeter signal and its fluctuations. An absorption profile reported by EDGES sparked excitement and debate because it was deeper than expected, possibly hinting at interactions between baryons and dark matter. Future measurements will refine our understanding of the early universe. The dynamics of dwarf galaxies and low surface brightness galaxies provide compelling dark matter evidence. These galaxies are dominated by dark matter, as their visible matter alone cannot explain observed velocities. Elliptical galaxies also exhibit mass profiles that require substantial dark matter halos to account for the motions of their stars. Dwarf spheroidal satellites of the Milky Way show especially large mass to light ratios, indicating that they are embedded in dense dark matter halos. Such systems serve as laboratories for studying dark matter properties on small scales. Gravitational lensing sometimes produces spectacular arcs and multiple images of background galaxies. When the alignment is near perfect, the lensed image forms a complete or partial ring, known as an Einstein ring. The detailed shape and brightness of these arcs reveal the mass distribution in the lensing galaxy or cluster. By modeling the lensing system, astronomers can infer the amount and distribution of dark matter required to reproduce the observations. Strong lensing thus offers both striking visuals and quantitative constraints on dark matter. Numerical simulations have transformed our understanding of structure formation. By modeling billions of particles under gravity, scientists can reproduce the cosmic web of filaments, walls, and voids seen in galaxy surveys. Cold dark matter simulations, like the Millennium and Bolshoi projects, predict a hierarchical buildup of structure, where small halos merge to form larger ones. Including baryonic processes such as star formation, supernova feedback, and black hole activity adds complexity but yields realistic galaxies. Discrepancies between simulations and observations on small scales motivate ongoing refinements. Direct detection experiments search for rare collisions between dark matter particles and atomic nuclei. Detectors filled with noble liquids or crystals are cooled and shielded deep underground to reduce background noise. When a dark matter particle scatters, it deposits a tiny amount of energy that can be detected as light, charge, or heat. Experiments like XENONNT LUX-ZEPLIN and Panda X have achieved incredible sensitivity, yet no definitive signal has emerged. As technology improves, experiments approach the neutrino floor, where solar and atmospheric neutrinos produce similar signatures. Indirect searches look for products of dark matter, annihilation, or decay. If dark matter particles annihilate, they could produce gamma rays, positrons, antiprotons, or neutrinos. Observatories such as the Fermi Gamma Ray Space Telescope, AMS-02, HESS, and IceCube monitor the sky for excesses above known astrophysical backgrounds. A tentative excess of gamma rays from the Galactic center sparked interest, but remains contested. Interpreting indirect signals requires careful modeling of astrophysical sources, making the task both challenging and intriguing. Particle colliders offer another avenue to search for dark matter. In high-energy collisions at the Large Hadron Collider, dark matter particles might be produced and escape the detectors, manifesting as missing energy. Physicists look for events in which momentum is not balanced, accompanied by jets, photons, or leptons. Although no compelling signals have been found, these searches place limits on the mass and coupling of potential dark matter candidates. Future colliders with higher energies and luminosities could probe deeper into parameter space. Beyond the canonical weakly interacting massive particles, theorists explore a diverse landscape of dark matter models. Sterile neutrinos, which do not interact via the weak force, could act as warm dark matter and address some small-scale structure issues. Ultralight axions with masses around 10 to the minus 22 electron volts would have wavelengths the size of galaxies, leading to fuzzy dark matter that suppresses small structures. Self-interacting dark matter proposes that dark matter particles scatter with each other, affecting halo cores and satellite abundances. Each model makes distinct predictions testable by astrophysical and laboratory experiments. Primordial black holes could form from extreme density fluctuations in the early universe. Depending on their mass, they might have evaporated by now, or could persist as a component of dark matter. Microlensing surveys like MACHO and EROS have constrained the abundance of black holes with masses around that of stars. Gravitational wave detections of black hole mergers by LIGO and Virgo have revived interest in primordial black holes with tens of solar masses. While unlikely to account for all dark matter, they remain an intriguing possibility. For years, astronomers were puzzled by the missing baryon problem. Observations of stars and gas accounted for only about half of the baryonic matter predicted by nucleosynthesis and the CMB. Simulations suggested that the missing baryons reside in a warm-hot intergalactic medium at temperatures of millions of degrees. Detecting this diffuse gas requires sensitive X-ray and ultraviolet observations. Recent detections of absorption lines from highly ionized oxygen along quasar sightlines have begun to locate the missing baryons. Completing the census of ordinary matter helps anchor cosmological models. Weak gravitational lensing by large-scale structure distorts the shapes of distant galaxies by tiny amounts. Measuring this cosmic shear requires averaging over millions of galaxies to detect coherent patterns. Surveys like the Dark Energy Survey, HyperSuPrimeCam, and the upcoming LSST map shear fields and infer the underlying matter distribution. Cosmic shear is sensitive to both the geometry of the universe and the growth of structure, providing a powerful probe of dark matter and dark energy. Careful control of instrumental systematics and intrinsic alignments is essential for this technique. Between the filaments and clusters of the cosmic web lie immense voids, regions with densities much lower than average. Voids occupy most of the universe's volume and influence the propagation of light and the motion of galaxies. Studying voids reveals how matter and dark matter are distributed on large scales and offers complementary constraints on cosmological models. Some theories predict that modified gravity effects are stronger in low-density environments, making voids laboratories for testing gravity. The emptiness of voids carries its own stories about cosmic evolution. Neutrinos are abundant but elusive, streaming through space with tiny masses. Oscillation experiments have shown that neutrinos come in three flavors that transform into one another, implying non-zero masses. Cosmology provides additional constraints. Massive neutrinos suppress the growth of structure on small scales because they free stream out of density perturbations. Measurements of the cosmic microwave background, galaxy clustering, and lensing limit the sum of neutrino masses to below a fraction of an electron volt. Combined with laboratory experiments, these cosmological bounds shape our understanding of the neutrino sector. Baryon acoustic oscillations are imprinted not only in the microwave background, but also in the large-scale distribution of galaxies. The sound waves that propagated in the early plasma set a preferred scale in the matter distribution after recombination. Measuring the BAO scale at different epochs provides a standard ruler that complements supernova standard candles. The interplay between BAO, supernovae, and CMB data breaks degeneracies among cosmological parameters and tightens the constraints on dark energy. This synergy exemplifies how diverse observations work together. Gravitational waves from inspiraling binary systems provide a new tool for measuring cosmic distances. The amplitude and frequency evolution of the gravitational wave signal encode the luminosity distance independently of the cosmic distance ladder. When a gravitational wave event has an electromagnetic counterpart, the redshift of the host galaxy can be determined, turning the event into a standard siren. The first such measurement came from the neutron star merger GW 170817. As detectors improve and more events are detected, standard sirens will offer an independent check on the Hubble constant and dark energy. Inflationary models predict a background of primordial gravitational waves that would leave a distinct B-mode pattern in the CMB polarization. Detecting these primordial waves would provide direct evidence for the inflationary paradigm and probe physics at energy scales far beyond those accessible on Earth. Experiments target the tensor to scalar ratio, which measures the relative strength of gravitational wave perturbations. Current limits place the ratio below a few percent, but future missions hope to improve sensitivity. The search for primordial gravitational waves exemplifies the interplay between cosmology and fundamental physics. Before the discovery of dark energy, cosmologists expected that the expansion of the universe should be slowing down under the gravitational pull of matter. In the early universe, radiation dominated the energy density, causing rapid deceleration. As matter took over, expansion continued, but at a decreasing rate. Around 5 billion years ago, dark energy became dominant, and the expansion began to accelerate. Observations thus reveal a dynamic history, with different components shaping the cosmic expansion at different epochs. One of the most direct probes of cosmic acceleration would be to measure the change in redshift of distant objects over time. Over decades, the redshift of a quasar or galaxy will change slightly as the universe expands more or less rapidly. This redshift drift is extremely small, on the order of centimeters per second per year. But future ultra-stable spectrographs on giant telescopes may detect it. Measuring redshift drift would provide a model-independent check on dark energy. The prospect of watching the universe's expansion in real time is a testament to the patience of cosmology. The ultimate fate of the cosmos is intertwined with the behavior of dark energy. If dark energy remains constant, galaxies will drift apart, stars will burn out, and black holes will evaporate over unimaginable timescales. If dark energy increases with time, a big rip may occur, tearing apart structures down to the atomic level. In a cyclic or bouncing cosmology, expansion could eventually reverse, leading to a big crunch, followed by another expansion. Each scenario inspires contemplation about impermanence and the long arc of cosmic evolution. Some physicists ponder whether the values of cosmological parameters are set by necessity or chance. The anthropic principle suggests that we observe a universe compatible with life, because only such a universe allows observers. In a multiverse framework, different regions might have different values of the cosmological constant or particle masses. While controversial, anthropic reasoning can offer explanations for why dark energy is small yet non-zero. These ideas blur the line between physics and philosophy and provoke deep reflection on existence. The modern era of astronomy embraces a multi-messenger approach. Photons, neutrinos, gravitational waves, and cosmic rays each carry unique information about cosmic phenomena. The simultaneous detection of gravitational waves and light from a neutron-star merger demonstrated the power of combining messengers. Future events may include neutrinos and gravitational waves from core collapse supernovae or gamma-ray bursts. By integrating diverse signals, scientists gain a richer, more resilient understanding of the universe. Every measurement in cosmology comes with uncertainties that reflect the limits of our instruments and knowledge. Quantifying and reducing these uncertainties is as important as the measurements themselves. Statistical fluctuations, systematic biases, and selection effects can all influence results. By openly reporting error bars and exploring different analyses, researchers build trust in the conclusions. This transparency fosters collaborative progress and ensures that we do not overinterpret hints and anomalies. Ultimately, the study of the cosmos is a human endeavor shaped by curiosity, imagination, and cooperation. The instruments we build are extensions of our senses, and the theories we craft are products of shared thought. As we look outward across billions of light years and back across billions of years, we also look inward at our capacity for wonder. The unknown components of the universe serve as reminders that science is an ongoing journey. Each generation adds a piece to the mosaic, mindful that the full picture may always remain just beyond reach. Measuring the age of the universe involves combining theoretical models with observations. The cosmic microwave background provides a snapshot at 380,000 years after the Big Bang, and the time since then is inferred by fitting cosmological parameters. Globular clusters, containing some of the oldest known stars, offer independent estimates of cosmic age. The current value of about 13.8 billion years arises from this convergence of methods. Along with the age comes the notion of a cosmic horizon, the maximum distance from which light has had time to reach us, beyond which the universe remains forever unknown to us. Because light travels at a finite speed, looking at distant objects is looking back in time. A galaxy observed at 1 billion light-years distance appears as it was 1 billion years ago. This look-back time allows astronomers to reconstruct cosmic history by observing galaxies at different distances. Deep surveys, such as the Hubble Ultra Deep Field, reveal galaxies forming in the first few 100 million years after the Big Bang. By studying objects across cosmic time, we witness how stars, galaxies, and large-scale structures evolve. Although the cosmic neutrino background has not yet been directly detected, several approaches are being pursued. One proposal uses the fact that relic neutrinos can interact with high-energy neutrinos from astrophysical sources, modifying their spectrum. Another approach involves capturing relic neutrinos on radioactive nuclei, a process that would produce a detectable signature. Experiments such as Ptolemy aim to build detectors sensitive enough to catch these faint interactions. Detecting the neutrino background would confirm a key prediction of the Big Bang and open a new window on the early universe. The cosmic microwave background spectrum is remarkably close to a perfect blackbody, but tiny deviations could reveal physical processes in the early universe. Energy release from decaying particles or early stars would distort the spectrum. creating mu-type and I-type distortions. Future missions, like Pixie and PRISM, plan to measure the spectrum with far greater precision, potentially detecting such distortions. Spectral distortions complement anisotropy measurements, probing the microphysical processes that occurred between recombination and reionization. These subtle signatures could provide clues about dark matter, annihilation, or decays. Combining different cosmological probes enhances the power of each. Cross-correlating galaxy surveys with weak lensing maps helps separate cosmic signals from observational noise. Correlating the cosmic microwave background lensing map with large-scale structure traces the growth of structure and the geometry of the universe. Cross-correlations also help calibrate galaxy bias, the difference between galaxy clustering and the underlying matter distribution. This synergy exemplifies how modern cosmology leverages multiple datasets to extract robust information. Large galaxy surveys have mapped the three-dimensional distribution of galaxies over vast volumes. The Sloan Digital Sky Survey, the Baryon Oscillation Spectroscopic Survey, and the extended BOSS program have measured the BAO scale with increasing precision. The detection of the BAO peak in the correlation function provides a standard ruler that helps determine distances and the expansion rate. These measurements have confirmed the predictions of the standard cosmological model and provided independent evidence for dark energy. Upcoming surveys will push these measurements to higher redshifts. Another approach to measuring the expansion history involves cosmic chronometers. Galaxies whose ages can be determined from stellar population models. By comparing the ages of galaxies at slightly different redshifts, the relative expansion rate can be inferred. This method is independent of standard candles and rulers, providing a complementary check on cosmological parameters. Along with the prospect of measuring redshift drift directly, cosmic chronometers represent the drive to develop novel techniques. The diversity of methods strengthens confidence in the resulting cosmology. The assumption that the universe is isotropic, that it looks the same in all directions, is a cornerstone of cosmology. Observations of the cosmic microwave background and large-scale structure generally support this. But small anomalies and directional asymmetries spark debate. Some studies have reported variations in the fine structure constant or hints of a cosmic dipole in supernova data. While these findings remain uncertain, they motivate careful scrutiny of datasets and the underlying assumptions. Testing isotropy is crucial because any large-scale anisotropy would challenge the foundations of the cosmological principle. Gravitational lensing not only probes dark matter, but also acts as a natural telescope. Massive clusters magnify and distort the light from distant galaxies behind them, allowing astronomers to study galaxies that would otherwise be too faint. Lensing has revealed some of the most distant galaxies known, providing glimpses of the universe when it was less than 1 billion years old. By combining lensing magnification with deep imaging, researchers piece together the formation of the earliest galaxies. This cosmic magnifying glass underscores the interconnectedness of structure and observation,